everybody, Emma Harper here, and this episode, it's the one that quietly rewires your entire reality. If you're driving, keep both hands on the wheel. No jumping to hyperspace till the credits. Today we ask the question you only whisper at 2 a.m. Are we alone? If not, why haven't they FaceTimed? And the real gut punch? Are we the new kids or the science fair project?
Dr. Nathan Cole checking in, astrophysicist, professional starer, and full-time giver of existential goosebumps. We're diving into where life actually came from, the odds it sparked on its own, and the wild card, maybe it was delivered, not just from another planet, but from another universe.
You heard that right. Panspermia, wormholes, ʻOumuamua weirdness, creepy patterns in our DNA, and the question I'm scared to ask, what if they already found us?
Zero tinfoil, 100% peer-reviewed. We'll walk from the first self-copying molecule to civilizations that can redesign whole realities.
Formats simple, bite-sized parts, maximum punch. We start with how did even Earth get life and end with who's watching and why the silent treatment.
Spoiler, nobody's out there is not required homework.
Still here? Awesome. Chills yet? Totally normal. This is Are We Alone? And we're kicking off with the most uncomfortable truth of all. What if life on Earth was never one of a kind and never meant to be? Part 1 drops in 3, 2, 1. Okay, we're starting with the moment that drives people nuts. Dead stuff to living stuff. No fairy dust, just rocks, oceans, volcanoes, lightning, to cells, DNA, us. Dr. Cole, no poetry. What's this prebiotic evolution everyone flexes?
Prebiotic evolution is evolution before evolution. No critters yet, but chemistry is already auditioning. Molecules pop in, crash, remix. Some stick around longer, some grab lunch better. Competition starts before the first bacterium even clocks in. Life didn't start from zero. It revved up during a billion-year chemical warm-up lap.
Sounds legit, but where's the on switch? Is there a, yep, that's alive line in the sand?
One magic moment. The first replicator. A molecule that copies itself using the junk around it. That's when information stops being a passenger and starts driving.
Like a Google Doc that hits Control-C, Control-V forever?
Nailed it. Here's the gut punch. To not fall apart in 2 seconds, that replicator needs roughly 2,000 links. That's 2,000 character source code that compiles and self-replicates.
2,000. That's like a monkey accidentally coding Photoshop and it runs.
If it was one try, yeah, impossible. But Earth wasn't a test tube, it was a planet-sized chemistry lab. Billions of liters of broth, millions of hot tubs, ice edges, clay copy machines running hundreds of millions of years.
So, tiny odds, but infinite lottery tickets.
Picture a casino where the jackpot is 1 in a trillion. One ticket? Forget it. Now give the planet quadrillions of new tickets every second for 500 million years. Jackpot stops being a miracle, it's Tuesday.
I'm not loving being called a statistical inevitability, but okay.
Get comfy. We're physics' side effect, not its prom date.
Ouch.
Bonus, the replicator probably started small. Short chains that helped neighbors stick, then moved into fat bubble apartments, protocells. Suddenly, all the freelance chemicals are locked in one room and forced to start a startup.
Life's first co-working space. Chaos to Series A funding.
Exactly. One day, the startup self-funds, self-copies, stores the playbook. Chemistry graduates to proto-life.
Hold up. Why did this happen so fast? Earth barely cools, oceans fill, boom, fossils. Lucky draw or red flag?
Perfect segue. Next up, how fast can evolution actually sprint, and the spicy theory that life was overnighted from Amazon space. Part 2 was life delivered. Seatbelts, people.
Okay, so Earth cools off, oceans settle, and bam, life boots up. Not a slow burn saga, more like someone hit quick start. Normal or sketchy?
Sketchy and huge. The gap between hell planet and microbes leaving receipts is geologically a coffee break. That's not trivia, that's a flashing neon clue.
Human translation, you move into a new apartment, cockroaches already have the Wi-Fi password.
Gross, but perfect. 2 headlines. A, life is easy mode. Liquid water plus energy plus organics plus stability equals ignition. Life isn't a unicorn, it's default software for wet rocks.
Universe factory settings equals alive. I want that on a hoodie.
B, life didn't start here, it landed. Panspermia is life or life starters hitchhiked on space rocks.
Panspermia sounds like a desert rave. Break it down.
Somewhere else, chemistry already had a head start. Asteroid smash, ejecta capsule, cruises space, crash lands on baby Earth, unzip biofolder.
So we're beta testers for someone else's app?
Exactly. Panspermia doesn't solve origin, it outsources it. We just move the mystery to another zip code.
But it does explain the speed, right? We didn't compile from scratch, we ran the installer.
Bingo. Scientists keep panspermia on the table because why so fast stops being a plot hole.
Real talk, can spores actually survive the trip? Space is radiation, vacuum, Antarctic cold.
Uncomfy, but doable. Some microbes go full hibernation, DNA crystal in a rock cocoon. Lab tests, they wake up after fake Mars trips. Million-year nap? Not sci-fi.
So life isn't a porcelain doll, it's the cockroach that survives nukes and your landlord.
Merch that. Life's default mode equals grabby survivor.
Big takeaway, Earth might just be one stop on the relay. Not the source code, just another server.
Exactly. Next question. Local delivery, planet to planet, galactic FedEx, or inter-universe Amazon Prime?
Part 3 teaser. We go galaxy size, how the Milky Way stirs the soup for billions of years, and why the haters call panspermia kicking the can down the cosmic road. Who packed the box, who hit send, and where's the next drop? Part 3, 2 minutes, don't touch that dial. Okay, brutal honesty time. Panspermia sounds slick. Life got delivered, mystery solved. Critics fire back, you didn't solve squat, you just moved the goalposts. Fair?
Dead on fair. Panspermia doesn't explain who wrote the first recipe. It explains how the recipe went viral. Logistics, not genesis.
So it's how the cookbook toured kitchens, not who wrote the cookbook.
Bingo. And those cookbooks can travel stupid far.
Spore survival still sounds like Star Trek. Walk me through it again for the skeptics and the cheap seats.
Not Trek, lab tested. Microbes hit panic mode. Squeeze out water, zip DNA in protein armor, metabolism off. Result, living USB stick. Radiation, ignored. Vacuum, yawn. Ice age, nap time.
So an asteroid chunk is FedEx with a passenger on pause.
Exactly. Asteroid smash, ejecta capsule, million-year cruise, splash down in new ocean, and, honey, I'm home.
We think life is delicate snowflake. Bacteria laugh, shoot me into space raw, I'll wait.
Life isn't fragile. It's stubborn code that refuses to die.
Scale check. Neighbor planets, Mars, Arrow, Earth, or next star over?
Both. Mars rocks already land here, fact. Comets, interstellar drifters. Gravity kick, rogue ice truck, new zip code.
Comets equal Windows XP wallpaper with biocargo.
Dirty, driverless Amazon van.
Mind blower. Galaxy's been stirring the pot for 12 billion years, older than our sun. Differential spin equals cosmic blender.
Milky Way equals giant soup kitchen. One lucky recipe drops in, supernovae, migrations, gravity slingshots, recipe spreads.
We're not the first customer, just one address on the route.
Nailed it. If this works, are we alone is a dumb question. Life equals galaxy-wide firmware update.
Creepy finale. Find alien life with our exact genetic grammar, not cousins, siblings.
DNA family reunion? Cosmic edition.
So who stabilized the template? Who hit deploy? Next up, was it nature or someone older than our star?
Part 4. Did seniors seed the galaxy on purpose? And if yes, where the hell are they? Spoiler, the answer isn't nowhere. It's way worse. 2 minutes, don't blink.
Okay, we've done Mars to Earth Uber. Now you're saying the entire galaxy is the driver. The Milky Way isn't just pretty wallpaper, it's a living conveyor belt?
100% conveyor belt. Our galactic disk, 12 billion years old. Sun, just a toddler at 4.5. We're the new condo in an ancient neighborhood.
Plot twist. We're the gentrifiers.
Exactly. And the disk doesn't spin like a vinyl record. Differential rotation. Inside laps faster, outside crawls. Result? Everything gets stretched, swirled, remixed for billions of years.
Galaxy equals cosmic Vitamix on permanent blend.
Supernova blast ingredients. Gravity slingshots ice cubes. Gas clouds migrate like food trucks. One kitchen nails the recipe, boom, franchised galaxy-wide.
So one lucky lab leak becomes every planet's starter kit.
Precisely. We're not the inventor of English. We're native speakers.
Ouch! We're not the spark, we're one candle in the relay.
Physics, not poetry. All it takes, one success story, pack it in a rock or comet, galaxy's 12 billion year stir cycle does the rest.
So Earth isn't Lab 1, we're Build 2.7.3.
Exactly. If galactic panspermia is real, similar planets equal similar biology. Same genetic grammar, different accents.
Find a Europa microbe that speaks our codons, not life exists. Hey, cousin.
DNA handshake across the spiral arms.
Gut check. We're grandkids of the Milky Way. So whose kid is the Milky Way? Can life jump universes like it jumps stars?
Part 5 Bridge. Modern cosmology says universes bud off like trees. Next, are we chemistry's accident or someone else's export from another reality?
Translation. Do we exist because physics said why not? Or because someone hit deploy in another universe?
Part 5 drops in 3, 2, 1.
Okay, one floor up. We've seen the galaxy mailing life like junk flyers. Now the rude question. Why should life ever spark once? Is it one in the cosmos jackpot and we're the only golden ticket?
Classic human glitch. We grade rarity, Earth style. 2000 link replicator by accident? Odds equal clown level tiny. But cosmology says stop thinking one planet. Think entire universe as the lab.
So one lottery ticket equals infinity tickets every second?
Exactly. Jackpot odds, 10 to the minus 400. Players, trillions of wet rocks. Runtime, billions of years, still ticking. Almost zero becomes, yep, someone's cashing in.
Romantic alert. You just turned we're special into we're stats. Rude.
Rude but real. Universe isn't cozy snow globe. It's absurdly huge. Galaxies? Sand grains. Earth-size rocks? Beach party. Question flips. How could life not pop somewhere?
People hear that and go, aha, we're the center anyway. Chosen ones vibe. Myth bust.
Anthropic Selection 101. You can only whine perfect settings from inside the one room that has oxygen. Dead universes, no complainers. You woke up in the hotel with Wi-Fi, obviously.
So we feel rare equals optical illusion. We're inside the jackpot, yelling jackpots never happen.
Poetry. Now mash it with Galactic FedEx. One hit recipe, then Galaxy copies and pastes. Life isn't one fireworks show. It's open source code.
Scary punchline. If it's that reproducible, where's the crowd? Where's everybody? You just proved we shouldn't be solo.
Cosmology's mic drop. Our universe might be one bubble in infinite foam. Infinite rolls equals every impossible event is guaranteed somewhere.
Translation. Someone beat us to the punch, maybe eons ago.
Before us, beside us, or way upstream.
Part 6, Bridge. Next, we dive into eternal chaotic inflation, universes spawning universes. Life isn't just passenger. Life might be the player hitting seed next server.
Part 6. Are we chemistry's oops or someone's export with tracking number? Spoiler, the tracking number might be in our DNA. Part 6. Are we chemistry's oops or someone's export with tracking number? Spoiler, the tracking number might be in our DNA.
Drivers, keep your eyes on the road. In 60 seconds, we read the shipping label. Part 6. Go. Any real clue life on Earth got Control-V'd by someone who already knew the cheat codes? Not bearded Sky Dad. Someone hit install and ghosted.
No Made in Andromeda tattoo, but one thing makes scientists argue in actual journals: our universal genetic dictionary.
The DNA to protein cheat sheet that every cell uses?
One table, planet-wide. Bacteria, redwoods, your cat, you, same 64 to 20 lookup. Not similar, identical. Like every device on Earth runs MP3.
One file format to rule them all.
And it's stupidly forgiving. Typo in DNA? 80% of the time the protein still works. Graceful degradation built in.
Biology says, oops, still runs. That's engineer energy, not random energy.
Two camps. Camp A, brutal evolution killed every sloppy code. Camp B, someone pinned the good version and airdropped it.
Camp B equals life runs on USB-C because USB-C won once.
Exactly. And guess what? We're already doing Camp B. CRISPR labs rewrite the dictionary. We add new amino acids. We freeze custom genomes. Roadmap to galactic seeding, 100 to 200 years, tops.
So a sieve a billion years ahead could have standardized biology and vanished. Code lives on.
They didn't sculpt humans. They open-sourced the engine. Evolution writes the DLC.
Spill the 3 a.m. Google bait.
Ready? Eternal inflation. Universes butt off universes. Infinite sequels, infinite physics tweaks, infinite rolls of the dice.
Infinite Netflix seasons.
In that multiverse, almost impossible equals Tuesday. Someone, somewhere, already cracked God mode bioengineering and hit export.
Translation, we're not the devs, we're running their EXE.
Their fingerprint isn't a saucer, it's the grammar in every cell.
Takeaway, we might be Season 3, Episode 9. Universe isn't a solo project, it's a franchise.
Part 7, Eternal Inflation Deep Dive. Infinite tries means impossible becomes inevitable. Guess who's the grandkid? 60 seconds. Lock in.
Buckle up. Does the universe itself have parents?
Short answer, some models say yes. Long answer, grab the oh shit handle.
Handle grabbed since Part 3. Hit me.
Eternal chaotic inflation. Sounds scary, tastes simple. Picture reality as bubble wrap. One bubble pops, new bubble inflates. Brand new universe, custom physics, and the popping never stops.
Big Bang equals franchise, not one-off.
Studio's been open forever. Our universe? Season 9,847,201.
We're not the pilot. We're mid-season filler.
Exactly. Every bubble gets its own gravity dial, particle menu, expansion speed. Some collapse in 3 seconds. Ours, Goldilocks Wi-Fi.
Cosmic A/B testing on steroids.
Now the gut punch. Rarity dies in infinity. One universe equals life equals miracle. Infinite universes equals life equals Tuesday.
We're special equals we're a data point.
Sims Kid mashing New Game Plus forever. Every possible outcome gets its own save file somewhere. Superintellects, bioengineers, seniors who seed baby universes for extra credit.
Rude. In another branch, middle schoolers already did this for science fair.
Possible. Takeaway. We're not lonely. We're the youngest sibling. Scary upgrade.
Old fear, we're alone in the dark. New fear, we're the kid at the adult table.
Nailed it. Inflation kills the drama of solitude, replaces it with, so, who's the senior here?
Next logical jump. If universes breed, and somewhere someone cracked life export, can you literally FedEx a bio kit through the family tree?
Physics says portals. Wormholes, black holes, real math.
Portal episode! Part 8. Can you slide a life flash drive from Mom Universe to Baby Us? Who already did? 60 seconds, portals charging. Practical panic. If senior civs existed, how the hell do you mail life to another universe? FedEx doesn't deliver to alternate realities.
2 cosmic chutes on the table. Wormholes, black holes.
Wormholes equals movie swirl tunnel to planet purple eyes.
Exactly. Einstein math says space-time can be stitched. 2 dots that are light years or whole universes apart get a private hallway. Not faster travel, shortcut travel. Door, not highway.
Level skip cheat code.
And the door doesn't have to stay in our universe. It can open on a whole different map.
Inter-universe Uber?
Possible. Payload options, PDF, here's the DNA cookbook. Lunchbox, frozen spores, ready to thaw.
Option A, recipe. Option B, takeout.
Black holes, scarier reputation. Pop culture, cosmic shredder. Physics, maybe a maternity ward. Some equations say fall in here, pop out in brand new baby universe.
Black holes are maternity wards for reality?
Live hypothesis. Drop a life seed packet near the lip, new cosmos boots up with your starter culture pre-installed.
TLDR, wormholes equal doors, black holes equal 3D printers for universes.
Advanced sieve recipe? Zip the bio file, yeet it into the right chute, new universe wakes up alive.
Life isn't a local blog. Life is a chain letter that learned to hop realities.
We're not the author. We're the latest forward.
2 burning questions. Still sci-fi? If portals work, where's the welcome committee?
Real papers, real math. Part 9. Portals are one-way tickets. They concede us, but nobody's coming to parent-teacher night. Part 9 drops in 60. Brace for You've Been Left on Red by Physics.
Most annoying plot twist. We've got wormhole blueprints. Cool. Why can't we just prop one open, drop a biocare package, and go say hi to the neighbors?
Meet the bouncer. Exotic matter. To keep the wormhole throat from snapping shut, you need negative energy struts, not dark energy, stuff that weighs less than vacuum.
Translation. Normal matter equals gravity hug, collapse. Exotic matter equals anti-hug. Hallway stays open.
Picture a tent flap. No poles, flop. Exotic matter is invisible carbon fiber poles.
Amazon link?
Wish list only. We've seen microflex, Casimir effect, 2-plate squeeze vacuum, tiny negative blip. But we need freight train loads, stable, sculptable. Current stock, 0.
Blueprint check, lumberyard empty.
Even with the lumber.
One sneeze, spaghetti passenger. One quantum hiccup, poof, it's holding a soap bubble in a hurricane.
Bottom line, exotic matter equals real physics word, industrial scale version equals unicorn tears.
So round-trip postcards? Nope. If a package ever slid through, the delivery guy ain't coming back.
Silence explained. Return to sender, address unknown.
Next stop, black holes, one-way escalators to baby universes, and why the down button works but the up button is melted.
Part 10 in 60. Keep your tray tables up.
Award-winning science reporter who never took physics. Interstellar flies around one and calls it a hallway. Movie magic or actual physics?
Both. Grab your latte, here's the 2-bucket version. Plain donut hole, Schwarzschild, perfectly round drop shaft. Cross the velvet rope, event horizon, no reverse gear. Every hallway ends at Singularity equals game over. Down elevator, 0 stops. Spinning donut hole, Kerr. Whole shaft doing 300 miles per hour barber pole twist. Outside edge, ergosphere wind tunnel. Center is ring, not dot. On paper, thread the ring like a freeway loop, pop out somewhere else. Could be Andromeda, could be Universe B.
Pretty. Why's real life a buzzkill?
Space is a construction zone in a hurricane. Falling junk slams every gate. Accretion disk is star-hot microwave. Tidal stretch equals U equals angel hair pasta. Even the gentle supermassive ones roast you with X-ray sunblock.
Interstellar report card.
A+ on Gargantua's glow up. Real disk looks like that. Time crawl near horizon, clocks legit slow-mo. Softer spaghettification on big spinners. F on radiation sauna, they left the oven on. Clean hallway, real one collapses in 0.2 seconds. Round trip ticket, causality rips it up.
So best case is one-way escalator. Tourist portal, nope.
Textbook jackpot is emergency fire exit. Real cosmos is 99.999% express down.
Emma, part 11, kid mode. Why the back button is melted and causality is the mean hall monitor. 60 seconds. Elevator music starting.
Award-winning science reporter who never took physics. Explain it like I still think quantum is a car repair shop. Why can't we just yo-yo back through wormhole or black hole hallway?
Here's the trick. Metro turnstile with spikes on the exit. Physics' #1 rule, cause, effect, never reverse. Break it and you get the grandpa paradox. Kill grandpa, no you, no murder, grandpa lives. There goes the neighborhood.
Like toast can't untoast?
Perfect. We call it the arrow of time. Near megagravity, that arrow gets welded pointing one way. Any reverse lane either doesn't exist on the map or collapses the second you try.
3 toddler-level stop signs?
Road markings, geometry, light cones only point forward. Your text, your spaceship, your scream, no reverse zip code. Gas money, exotic matter. Need negative energy tankers to prop the hall open. Run dry, slam. Hall monitor paradox patrol. If you could high-five baby you, reality blue screens. Universe auto-deletes time loops like bad code.
So the building blueprint forgot the back door. Not our fault.
Nailed it. Best case, one-way mailbox. Drop the letter, DNA, spores, yo emoji, gone. Reach in, hand stays in.
Creepy upside? Whoever mailed us can't check the tracking number. Silence is physics, not snub.
Exactly. Part 12 flip. If inbox works, outbox works. Are we ready to forward the chain letter? 60 seconds. Your move, humanity.
A case locked. Forward open? Can we actually mail life onward like a cosmic relay?
Hell yes, 3 difficulty tiers.
Game on. Walk me through.
Level 1, soft mail, panspermia. Grab freeze-dried spores, seal in a hockey puck capsule, yeet into a comet tail. Galaxy is slow UPS. A million years later, new planet, new tenants. Cost, a Falcon 9 and a 6-pack.
Seeds in a tin can down the river. Love it!
Level 2, PDF mail. Send the recipe, not the cake. Laser blast a 3 GB file. Dear Alpha Centauri, here's Earth's starter culture. Print locally. Hardware, big dish and big check. Timeline, 2030s happy hour.
Imagine it like building IKEA furniture on a different planet, but the instructions are in a different language. Level 2, IKEA is able to use an alien toolbox. IT department approved.
Level 3, hard mail. Bridges. Stuff the capsule into a wormhole slot or black hole birth canal. One-way express to Baby Universe 47b. Tracking number? None. Status? Delivered? Somewhere.
Drop the mic. Package gone.
Drivers, don't skip this episode. Every Comet headline, every laser ping project just got plot armor. Your brain firmware just upgraded.
Real talk. My lifetime odds?
Level 1, 20 to 30 years. Level 2, 10 to 15 years. Level 3, grandkids problem. We're already the export beta.
We were imported. Time to hit send.
Part 13 hook? If someone standardized life before us, they signed the zip file. Next, DNA Easter eggs. What to hunt, why it's lab coat science, not tinfoil. 60 seconds. Grab your sequencer.
Clickbait alert, alien signature found in your genes. Late night cable or real lab talk?
Real lab, zero tinfoil. Here's the cheat sheet every Earth critter shares. 64 codons, 20 amino acids. Think IKEA manual that works for bacteria, redwoods, and your Uncle Bob. 2 red flags scream too neat. Bulletproof typos. DNA hiccups 99% of the time swap lemon for lime, not engine for banana. Code is forgiving AF. Symmetry porn. The table looks like Pantone swatches. Rows mirror, corners rhyme. Random? Nah.
Pretty doesn't equal engineered. How do we stat slam this?
We play cosmic bingo with a supercomputer. Shuffle 10 million fake codes, same rules, 3 stop signs, same chemical vibe. Basically Monopoly with real money rules. Grade every board. How many get our exact mirror pattern? If ours wins the lottery 1 in a billion times, raise an eyebrow. Pre-register the bet. No, look a cloud shaped like Elvis. We publish the pattern before we hunt. Science referee approved.
What's not a signature?
777 shows up. Las Vegas slot machine. Sum equals 42. Hitchhiker fanfiction. Real signature is watermark on every dollar bill, not a doodle.
Could a senior civ actually plant one?
Easy mode. Drop the watermark in the master template, the 64 square table. Every kid, grandkid, great bacteria inherits the logo. Free advertising forever.
My to-do list, no spaceship required?
Run the bingo tournament. Already happening. Find alien pond scum. Check if it speaks Earth grammar. Match is cousins. Different but still tidy? 2 different designers.
Part 14 teaser. Next stop, cosmic speed dating. Is the universe 21 and still in grad school, or 42 billion and already retired? Why your birth year rewrites the whole suspect list. 60 seconds. Grab popcorn. The timeline just got spicy. I'm still trying to wrap my head around the cosmic calendar. How much time do we even have for evolution? Is the universe old or young?
Surprise. It's both. Depends on your scale. In our version of reality, the universe is about 13.8 billion years old since the Big Bang. That sounds ancient to us, but on the life timeline, it's still early morning.
Early morning? I thought we were in the after-party cleanup phase.
Nope. Think of it this way. Stars are like light bulbs with different wattages. The bright ones burn out fast, but then there are red dwarfs, small, energy-efficient bulbs. They can shine for trillions of years. Planets around them, potentially long-term leases for life. So the main window for evolution is ahead, not behind us.
So if the universe were a TV series, we're in episode 1?
We're in the pre-credits. Earth and humanity are the early birds who showed up before the trailers. Most life stories haven't even started rolling yet.
Then here's the weird question. If there's so much time, why are we already here? Isn't it too early for intelligent life?
Great question. 2 honest answers. 1, we're the early risers. We just got lucky with the right combo, star, planet, chemistry. Sometimes the toast browns faster. 2, observer selection. We're seeing the moment when it's possible to see. If complex life only emerged later, we wouldn't be here to wonder about it.
And what about your big scary idea, the multiverse? There's even more time there, right?
In models like eternal inflation, parent universes can spawn daughter ones. That creates long family trees, chains of worlds where the laws of physics shift slightly, but the overall process keeps going. In that picture, evolution isn't just on planets. It can happen at the universe level. Some places kickstart life earlier, some later, some are better tuned for complexity.
Give me one image to remember that by.
Picture a forest where each tree is a universe. Some are young, some ancient, some cast deep shade, others let in more light. Life is like a species of forest creature that moves from clearing to clearing if it finds a way. Our tree is young, but the forest is vast, and some trees may have grown very old already.
And if creatures in one of those old trees figured out how to move to the next one, they could have influenced our little clearing?
Exactly. That's a polite way of saying, yes, evolution could have started long ago, long enough to learn how to pass the code of life forward, shaping the landscape of the multiverse.
So the takeaway for our listeners is our universe is young, the main seasons of life are still ahead, but that doesn't rule out that someone older may have already taken steps we can only dream of. And if that's true, the question, where is everyone, becomes, where are they here and how do we look?
And that's our bridge to part 15. Why, in this scenario, the search for extraterrestrial civilizations isn't just a romantic whim, it's a logical next step. We'll talk about how the regularity of cosmic processes removes the miracle from the equation and gives us a reason to search systematically.
Okay, we've talked so much about odds and scale, but here's my simple question. It all sounds poetic, but isn't this just a maybe we'll get lucky kind of thing? Why is it even rational to search for extraterrestrial civilizations instead of leaving that to philosophers?
Because in our worldview, miracles are off the table. We're not banking on a one-time lucky break. We're betting on regularity. Lots of stars, lots of planets, lots of chemical kitchens, lots of chances. When you've got tons of processes over long periods, rare outcomes become expected. This isn't gambling, it's statistics.
Give me an example I can picture.
Imagine an airport at rush hour. One flight, that's luck. It might land, it might not. But when you've got thousands of flights every day, you expect regular landings. Same here. With billions of flights of evolution, we expect to spot a plane, a signal, an artifact, a structure that nature alone can't explain.
So we're not chasing a miracle, we're chasing a scale effect.
Exactly. Quote of the day, what can't not happen eventually does if you give it enough time and tries. So the question shifts from do they even exist to where exactly are they and how do they show themselves?
Okay, so what counts as regular in this search? No mysticism.
3 pillars. Energy. Any civilization burns something. Heat, radio, lasers, megastructures all leave a signature. Engineering. Big systems are hard to hide, like planet-scale solar farms, weird transits, unusual dust, like spotting a construction crane on the skyline. And communication. If someone wants to be noticed, the cheapest way is narrow, clear beacons, radio signals, optical pings, repeating frequencies.
Sounds like a checklist. What are we doing practically?
3 lines of attack. Radio, long observations of narrow bands looking for repeatability and Doppler shifts. We're hunting for artificial clarity in the signal. Optics, Short, powerful flashes, laser pings, easier to spot against the noisy star background, and stellar photometry. We look for non-planetary transits, odd shapes, jagged edges, dust with strange properties, possible hints of engineered structures.
And how do we know we found a neighbor and not just nature doing its thing?
The three filters principle. Physics. Can this be explained by known processes? Dust, spots, glare. Repeatability. Can we predict it and see it again? Information. Does it carry a pattern that's easy to reproduce and hard to confuse, like a simple sequence of prime numbers in a laser?
Okay, but where's the role for me as a listener? I'm not building a telescope.
Your role? Don't skip episodes like this and keep an eye on real projects. News about new optical networks, sky surveys, catalogs of weird transits. That's not hype. It's like airport reports. The more flights we track, the better the chance of a landing. And yes, public attention equals funding, equals more eyes.
So the plan is we ditch the miracle, lean on regularity, run clear tests, and just search systematically.
Exactly. That clears up Fermi's romantic confusion. Where is everybody? The answer, probably somewhere. It's just a matter of our tools and patience. We need to catch a trace where statistics say it should show up.
Then let's go. In part 16, we shine a spotlight on the trickiest question. If they almost certainly exist, why can't we point to a spot on the map and say, intelligent life, right here? Where exactly should we look? And why is it harder than it sounds?
We've said huge scale, tons of chances, so many times, that I've got a blunt question. With all that math, do they exist even still a question?
Honestly, no. In our worldview, it's no longer a matter of belief, but an expected outcome. Intelligence should be out there somewhere. Cosmology tells us lots of platforms, lots of time, repeating processes. So the basic question is off the table. The real question is, where exactly are they in our galaxy, and how do we spot them?
Okay, where sounds like give me an address. Why don't we see a glowing sign that says, aliens here?
Imagine the ocean is real, so fish must exist. But you're standing on a pier with a bucket, staring at the same wave for 10 seconds a day. The problem isn't the fish, it's the method. In SETI, there are three major bottlenecks. When to look, timing. If a civilization sends a beacon only once a day for 1 minute, we'll likely miss it. It's like trying to spot a lighthouse that blinks once at night while you're scanning the horizon in daylight. Where to look, direction. The sky isn't a few stars, it's millions of directions, and beams, radio, laser, are narrow, like a laser pointer. If you're not in the beam, you see silence. And what language frequency to listen to, bandwidth. We've historically loved radio, but there could be optical pulses, infrared engineering signatures, even heat trails from massive systems. If you're tuned to FM and they're broadcasting in optics, you'll hear nothing.
So silence doesn't mean no one's there. It means wrong channel, wrong time, wrong spot. How do we start narrowing down the addresses?
We shrink the search space using common sense. A galactic habitable zone, not too close to the center, radiation mess, not too far out, low metal content. Our sun sits in the sweet spot. We look for similar neighborhoods and long-lived stars. Long-lasting bulbs. Red dwarfs burn for trillions of years, tons of time for development. But they're moody with flares, so we pick calmer systems. Engineering traces. We're not looking for hello Earthlings, but technosignatures, weird transits, non-planet shapes, unusual dust, narrow repeating pulses, even extra heat from large structures.
And if they exist, does that mean another galaxy or closer?
Most likely inside the Milky Way. Broadcasting powerfully across millions of light years is expensive. It's more logical that their signals or traces are within tens of thousands of light years, not in a neighbor galaxy. So the address is our home, the Milky Way, the neighborhood is stars no worse than the sun, and the marker is narrow, repeating, efficient.
That actually sounds grounded.
even boring in a good way. We're not chasing mysticism, we're chasing regular signs of tech.
Exactly. And here's another twist. If life really spreads, instead of being reinvented from scratch every time, we get a testable clue. In similar conditions, life should emerge with similar molecular grammar. If we find alien microbiology and see same basic code logic, it's not just they exist, it's there are distant relatives.
That's a beautiful bridge to the next topic. Lots of Earth-like planets doesn't mean life starts from scratch on each one. Maybe life gets carried, and then different worlds share the same root system.
Exactly. In Part 17, we'll explore why, even with plenty of land, life might not start independently, and how a galactic scenario predicts a shared molecular genetic foundation among those we might one day discover.
You keep saying there are tons of Earth-like planets, plenty of water, decent temperatures. Okay, then here's my blunt question. Why don't we see life everywhere? Why isn't every other planet bubbling, waving a microscopic flag saying, hey, I'm here?
Because Earth-like planet doesn't mean life automatically assembles itself. Conditions are just the stage. But the appearance of the first self-replicating system, that's not just, we've got water, let's party. It's still a very tough nut to crack. Let's break it down. Having a kitchen doesn't mean knowing how to cook. You might have a stove, sink, and pots, but if no one ever showed you how to make dough, you're not getting lasagna just because your kitchen looks nice.
So a just right ocean is just the kitchen, but the recipe for life doesn't have to reinvent itself in every kitchen.
Exactly. And here are two scenarios. Scenario 1, local and romantic. Each planet brews its own soup of life from scratch. Chemistry experiments, a replicator randomly emerges, it stabilizes, and evolution crawls forward. Problem. This might be a freakishly rare event. Maybe 1 in a billion planets pulls it off. Scenario 2, galactic, less romantic, more brutal. Somewhere, sometime, it already happened. Once. The working dough, the first stable code of life, was found. And then that dough got spread around to other ovens, other kitchens, over billions of years, via comet impacts, rock ejections, icy fragments, interstellar objects. So not every kitchen invents dough. Some just get it delivered.
I love that metaphor. So life isn't every farmer grows their own wheat. It's one bakery long ago handed out sourdough starter and we're all still baking with it.
That's almost perfect. And here's the key idea. If that bakery, the original source of living code, wasn't here on Earth, but somewhere else in the galaxy, or even earlier in another branch of reality, then Earth isn't the birthplace. Earth is the recipient, meaning life on Earth doesn't have to be local. It could be imported.
And that explains two things at once. Why life appeared here so fast after Earth cooled, because it wasn't origin, it was deployment. And why other similar planets might be empty, because the dough just hasn't reached them yet.
Exactly. It's a shift in thinking. No life doesn't mean life is impossible. Sometimes it's just not delivered yet. So the galactic scenario says life doesn't have to originate on every warm, rocky planet. It just needs to be replicated to wherever physics allows it to travel.
That sounds eerily technological. Like the galaxy isn't just tossing rocks around, it's running logistics.
And now, here's the juicy part. This scenario has a consequence we can actually test. This isn't philosophy, this is observable. If life is one starter, one base recipe spread across different planets, then life in similar conditions should share the same molecular genetic foundation. Translation: if we find alien microlife, really find it, not sci-fi, but say in the subsurface ocean of Europa or Enceladus or inside a meteorite, and we start examining how it stores and reads information, how it codes proteins, how it fixes errors. If we see the same coding logic as Earth life, not the same proteins, not the same organisms, not little guys with eyes, but the same grammar of the code, then that means something shockingly direct. We're relatives.
So we could literally say, hey, this bacterium from hypothetical Europa isn't just alien. It's our distant cousin from a great-great-grandparent who maybe wasn't even from this solar system.
Exactly. That's not we found life in the universe. That's we found part of our family.
And what if we find life that's built totally differently? No DNA, no RNA, no familiar coding logic.
Then we've got two mind-blowing options. Option A, life really can originate independently, different bakeries in different places. That means the universe doesn't just produce one biological style, but several. Or option B, someone, somewhere, played engineer and intentionally built a different standard, distinct from ours. And either way, it would be the biggest discovery in the history of science, bigger than just we're not alone.
So it's like either we're all descendants of one original chef, or the galaxy has multiple culinary schools, each with its own menu.
That's exactly it. You just summed up what academic papers usually stretch across 40 pages. And that's why we take missions to find microbial life, water, and organics seriously. Not just like, let's look for gray ships over Washington. Because the biggest clue might not be in a radio signal from a smart alien, but in a half-millimeter smear of slime under the ice of a foreign moon.
So the answer to "Are we alone?" might not come as an alien gave an interview to CNN, but as these microbes speak our genetic language.
Exactly. That would be the moment when human philosophy lays down and says, rewrite me.
Then I want to say this out loud for our listeners so it sinks in. If we ever find a similar code in alien life, that's almost a legal confirmation. We're not native. We're imports. We were delivered.
Yes, and that smoothly takes us to part 18. Because next we move from theory to actual hardware. In part 18, we talk about real interstellar objects that have already entered our solar system, ʻOumuamua, Three-Eye Atlas, and ask, could they be the delivery trucks, accidental or not, that carry material between stars?
Okay, you promised us real couriers. Let's name names. We know ʻOumuamua from 2017, Borisov from 2019, and now the newest guest, Three-Eye ATLS?
Exactly. It's the third confirmed interstellar object. Discovered in July 2025 by the Atlas telescope in Chile. Picture a leaf blown into a hallway by a gust of wind. Its trajectory and speed clearly show it's not local. It came from outside and is just passing through.
And it was actually photographed near Mars?
Yes, on October 3rd, the Mars orbiter ExoMars TGO, using its Cassis camera, captured it. Distance about 30 million kilometers, 19 million miles from Mars. It's an incredibly faint target, 10,000 to 100,000 times dimmer than typical objects for that camera. So scientists stacked many short exposures to pull it out of the noise. Earlier, Hubble caught it, July-August, and November-December, JUICE joins in, followed by Juno. Listeners, don't scroll past these headlines. These are rare snapshots of an interstellar visitor in the wild.
And what makes it not like the others? Give it to me straight, with vivid comparisons.
Let's break it down. First, water. Way too early. The Swift Space Telescope detected ultraviolet traces of OH, a breakdown product of water vapor. and it caught it far from the Sun, about 2.9 AU, almost 3 times Earth's distance. Estimated output 40 kilograms of water per second, like a fire hydrant on full blast. That's unusually early. Water vapor usually kicks in closer to the Sun. Looks like tiny icy grains are heating up and evaporating off the surface, feeding a thin coma.
Second, unusual composition.
Data from JWST and other spectra show lots of CO2. Estimates suggest a CO2 to H2O ratio of about 8 to 1, meaning dry ice dominates, water is weaker. That hints it came from a very cold zone in its original planetary disk, a place where CO2 can easily freeze and stick around.
Third, anti-tail to regular tail.
In summer, July-August, images showed a glow stretching toward the Sun, an anti-tail. That's weird. Dust usually trails away from the Sun. By September, it flipped to a normal tail. Kitchen analogy, early on, the coma was dominated by light icy grains that reflect sunlight and create a geometric illusion of a tail toward the Sun. Later, near perihelion, heavier dust took over and the tail behaved as expected.
Fourth, odd spectral lines.
Visible UV spectra showed nickel but no iron, rare for comets. Plus, reports of a bluish tint near perihelion. Comet dust usually reddens light. Translation, Atlas's dust chemistry and grain structure are atypical. This object breaks the mold.
And 5, large and ancient.
Hubble estimates the nucleus diameter at 5 to 6 kilometers, mass in the tens of billions of tons, around more than 33 billion tons. Some estimates suggest it could be the oldest comet ever observed, billions of years older than our solar system, like a message in a bottle from another planetary childhood. And fast and smooth. Speed about 210,000 kilometers per hour. Trajectory nearly flat and straight through our system. For observers, it's like a train with no stops. You spot it, and it's already leaving.
So, listeners, to remember, we've got a comet from another stellar kitchen. Started leaking water early, loves CO2, switched from anti-tail to regular tail, and overall, it's a bit of a weirdo. Doesn't mean flying saucer, but it does mean watch closely.
Exactly. And importantly, no threat to Earth. Perihelion passed in late October between Mars and Earth's orbits. It dipped toward the Sun and got lost in the glare, then re-emerged mid-November, and by December 19, 2025, conditions will be ideal for big telescopes. Scientists are watching to see how the chemistry evolves. Will the hydrant keep flowing? Will other volatiles join in?
Why is everyone so obsessed with these interstellar ones? We've got plenty of our own comets.
Because each of these guests is like a test tube from someone else's lab. ʻOumuamua had almost no gas, behaved like a dry shard. Borisov was rich in CO, like a super cold object. 3I Atlas gave early water and lots of CO2. Different disks, different chemistry. We're basically comparing recipes for comet dough across planetary systems, and that's directly tied to how water, carbon, and nitrogen, ingredients for life, move around the galaxy.
So what's next? We chase these things?
That's the dream for the near future. Technically, it's possible to intercept the next interstellar object. We'd need early detection, a fast launch, gravity assists, maybe hybrid propulsion, then fly by with spectrometers. And if one day we get close and see not just ice and dust, but say ultra-thin layered panels or strange grains, then we start reading the story of its home turf through its materials.
Got it. Listeners, don't skip episodes like this. This is the dry data that later turns into the biggest discoveries.
And in Part 19, we'll continue how to plan the hunt for interstellar leaves, where to stand by the roadside, how to chase, and why science now sees this not as sci-fi, but as an engineering challenge fit for an international mission. I can translate Part 19 next with the same tone and precision. Just say when you're ready.
We keep saying we should chase one of these objects and get a close-up look. Is that actually doable, or is it one of those someday dreams?
It's doable. No warp drives, no sci-fi magic, just solid, beautiful engineering. Picture a highway. A foreign truck with no plates, an interstellar object, is speeding through. To catch it, you need three things: early radar, a car that launches fast, and the right on-ramp.
Translate that from engineer speak.
Sure, here's your hunt checklist. Early detection. We need a radar that spots faint objects months before they pass by. That means survey telescopes and space cameras that can catch tiny dust specks against the starry background. The earlier we spot it, the easier the trajectory planning. Fast launch. Launch on alert. The rocket and probe need to be ready in storage. Our window is weeks, not years. Ideally, we have a universal interceptor, a probe body with standard instruments just waiting for its moment. Propulsion and trajectory. This is a mix of chemical thrust, quick kickoff, plus electric propulsion, slow, efficient acceleration and fine-tuning, plus gravity assists from Earth, Venus, or Mars, free slingshots. In the dream setup, solar sail, a lightweight wind catcher pushed by sunlight, like flying a kite on a tailwind, almost no fuel needed. An intercept profile. Two modes: flyby, zoom in within hundreds or tens of kilometers, snap like crazy. Cheap and doable for the next one. Rendezvous, match speed and fly alongside. Harder and slower, needs low relative velocity, more fuel or sail time. Payload, minimal but precise. Wide angle plus portrait cameras. Spectrometers, visible IR, UV to decode ice, gas, dust. Dust analyzer or mass spectrometer to grab particles. Magnetometer or dust meter to study the surrounding environment. And narrow beam radio beacon to keep contact when adrenaline spikes.
Sounds like a spy kit in a shoebox. Where are the bottlenecks?
Three big ones. Timing. We spot these visitors late. If the window is just a couple of weeks and the probe's still on paper, we miss it. Speed. They fly crazy fast. One mistake and you're waving at the tail instead of getting a close-up. And lighting? Near the sun, glare, radiation, heat. Instruments need to be like paparazzi with sunshades.
And where's Elon Musk in all this? He loves fast and bold.
SpaceX is great for launch vehicles, fast liftoff, decent payload, but they don't have a magic probe. Intercepting is a global team effort. Someone provides the rocket, someone the probe, someone the telescope time. That's why there's no business case yet. You don't get direct profit. It's about scientific prestige and dual-use tech like navigation, comms, and materials.
So the plan for the next few years is don't wait for a miracle, start building the kit now.
Exactly. A practical roadmap. A radar network, survey scopes plus space coronagraphs, early detection. An interceptor on standby, launch on alert. Hybrid propulsion, fast push plus fine-tuning. Flyby first, close-up images and spectra. Rendezvous later when we catch a good candidate, slow science up close.
If it all works and we get close, what's the dream prize?
Material and geometry. Thickness and layering of dust and ice. Gas composition, grain structure, that's the passport to its home disk. And if we spot unusually thin, layered, long-lasting flakes, the debate begins. Exotic chemistry or even technosignatures. But first, cold facts, not flashy headlines.
And listeners, reminder, subscribe to the podcast so you don't miss what's next. Every episode is like a new notch on the map. We're genuinely close to the moment when humanity looks an interstellar visitor in the face.
Coming up in part 20, we'll break down the data we've already gathered on these guests, color, water, gas, oddities, and why one clean spectrum can be worth 1,000 pretty pictures.
Emma, let's do this as a back and forth. Compare our three tourists and spend extra time on Atlas. It's the one currently passing through.
Deal. Quick frame. ʻOumuamua, 2017. Dry, no obvious tail, but a slight non-gravitational acceleration, like solar light giving a tiny push to an ultralight potato chip. Borisov, 2019. Basically a classic comet. Heavy outgassing, lots of CO. Atlas, 2025. A third type. Early water plus CO2 dominance and several oddities.
Okay, zoom on Atlas. What's this early water business?
The Swift Space Telescope caught ultraviolet OH, the UV echo of water vapor, when the comet was about 2.9 AU from the Sun, almost 3 times Earth's distance. Estimated outgassing is about 40 kilograms per second. That's a fire hydrant level, but it's happening too far out for a normal comet. Likely explanation: tiny icy grains got knocked off the surface, heat up, and rapidly sublimate, feeding the faint coma.
And chemistry. You said CO2 is running the show.
Right. Spectra, JWST and SphereX, indicate CO2 H2O 8:1, a rare ratio for our familiar comets. So Atlas likely formed in a very cold region of its parent disk where dry ice, CO2, freezes and stays put.
And the weird stuff, that's the anti-tail story, right?
Exactly. In summer, July, August, Hubble and ground telescopes saw a stretch of glow toward the Sun, an anti-tail. By September, the scene switched to a normal tail pointing away from the Sun. In plain terms, early on, scattering was dominated by light icy grains that produced a geometric toward-Sun effect. As activity rose near perihelion, heavier dust took over and the tail behaved normally.
And the nickel without iron and a blue tint?
Yes, visible UV spectra registered nickel lines with little or no iron, unusual. And near perihelion, parts of the object looked bluer than the Sun. Odd, because dust normally reddens light. Altogether, this points to atypical grain properties or emission processes. Atlas is an outlier.
Give us the hard observational facts. Where was it actually seen and how?
Good list. On October 3rd, ExoMars TGO CISS imaged the interstellar guest from roughly 30 million kilometers, 19 million miles, from Mars. The target was 10,000 to 100,000 times fainter than usual, so frames were stacked in 5-second slices to pull the signal out. When it plunged into solar glare, coronagraphs picked it up: SOHO LASCO, Stereo SETI, and GOES CAC-1. CCRI-1 estimated a coma up to 300,000 kilometers. Photometry recorded a very rapid brightening near the Sun, roughly scaling like R to the -7.5, much steeper than typical dusty comets. Orbital dynamics and early constraints give mass estimates much greater than 33 billion tons, nucleus diameter about 6 kilometers, and speed about 210,000 kilometers per hour. It may be billions of years older than our system.
And timeline for listeners in the car. What's already happened and what's next?
Perihelion, late October, between Mars and Earth orbits. It went into solar glare and re-emerged after mid-November. Best Earth window around 19 December 2025, HST and JWST. Observers involved or attempting: ExoMars TGO, JUICE, started early November, later Juno. IAWN coordinates monitoring roughly from 27 November through end of January. And yes, no threat to Earth.
Compare personalities: ʻOumuamua, dry and light; Borisov, gas-rich classic; Atlas, a CO2 heavyweight with early water and odd optics. What does that tell us?
That comet recipes vary between stellar systems. ʻOumuamua is the dry chip, Borisov is the cold gas comet, Atlas is the CO2 kitchen with a distant water hydrant and theatrical effects. Comets are couriers of water, carbon, oxygen, nitrogen, so we're literally studying how life's ingredients travel across the galaxy.
The intrigue remains about Atlas's non-gravitational effects. We'll see from December data whether there's enough gas to explain them naturally. If yes, case closed. If not, alternative explanations get debated.
Exactly. Science is data first, conclusions second. December spectra are crucial. They'll tell us what is evaporating and whether that matches the observed dynamics.
Final note for today, listeners, don't miss the updates. Subscribe to the podcast to catch fresh spectra and images of Atlas. This is a rare moment when we read a live note from another star system.
And in part 21, we'll go further. Given the universe had so much time, could a superintelligence have arisen that not only sows life but leaves traces in genetic code? And how do we test that carefully without veering into mysticism?
Nathan, you promised a bombshell. If the universe had plenty of time, could someone super smart have shown up and batch-mailed life around?
Frankly, yes, it's plausible. Call the idea the publisher of life. Imagine a civilization for which synthetic biology is as routine as making a PDF. Grab a template, package it, send it out.
Wow. Where would such a publisher leave an autograph? With a marker on the moon? We were here?
Much smarter, inside the genetic code, not in some random gene that can mutate away, but in the actual translation table, how DNA triplets map to amino acids. That table is the global standard for Earth life, and if you tuck a mark into it carefully, the mark can survive billions of years.
So, a watermark on the banknote that's part of the paper itself?
Perfect. Important caveat. Don't confuse natural elegance with an autograph. A true signature must meet 3 tests. It's not required for survival, no direct biochemical advantage. It's rare among the millions of possible alternative codes, and it's stable across all branches of life, so it's ancient.
How do we test this without tinfoil hats?
Like scientists, generate millions of alternative genetic codes under the same constraints: stop codons, redundancy, and chemistry. Pre-declare the signature criterion, say a specific arithmetic regularity or checksum, so we don't retroactively find patterns. Then do the stats. If our code shows a pattern that appears in only 1 in a million alternatives, that's worth discussing. If it shows up often, nature can make it by itself.
Do we even know how to make such signatures ourselves?
We're starting to. Labs already create expanded genetic alphabets and modified codon to amino acid tables. So the idea of standardizing and signing is technically realistic for a civilization older than ours.
Why would a publisher sign it all? Vanity?
Less vanity, more compatibility guarantee. If you distribute life like a platform, you'd embed a recognizable structure so future finders know this is a standard. You can work with it. Think USB, a known form factor and protocol.
Alternatives to hiding a mark in the code, like sending instructions instead.
There are 3 delivery channels: material, capsules of spores, cryosamples, seeds in envelopes. Informational, broadcast sequences as data, radio or laser. A receiver could print them on a future biofabricator. Geometric or engineering, exotic options like hypothetical bridges, very speculative and usually one way.
You're touching on the multiverse here, right?
Yes, if there are many universes, a publisher gets vast test beds and time. They could seed standards repeatedly across halls, and we would only see the local outcome, a shared code in our biosphere, and maybe matches elsewhere.
Practical instruments. What 2 concrete tests can we do soon?
Find alien microbes, Europa, Enceladus, meteorites, and compare their coding grammar. Identical logic of reading, repair, and table equals kin. Different, but strikingly deliberate, a mysterious alien school. Large-scale computations over alternative codes with honest p-values. If our code is statistically over-decorated to a pre-declared template, that supports the signed standard idea.
If a signature turns up, pray or send thanks?
Neither. It's an invitation to join the grown-ups table. Learn how to spread life responsibly. Don't contaminate other biospheres, respect local biology, enforce biosafety and transparent verification. Move from passengers to co-publishers.
One line for commuters.
If a superintelligence is the publisher, its best calling card isn't a plaque on Mars, but a statistically rare structure embedded in the language of life itself. That's testable, not worshipable.
Got it. Next up, are exact copies of us anywhere out there? Or is that a nice daydream? We'll ask what statistics and cosmology say. Don't go anywhere. Subscribe so you catch the next episode.
Nathan, straight up. Is there a copy of me out in the universe? The same laugh, the same coffee stain on the shirt?
Short answer, almost certainly not within our observable universe. Longer answer, maybe somewhere, but with caveats. Let's peel the layers.
Layers, I like that. First layer?
The first layer is finite volume, enormous complexity. To get a molecular perfect duplicate of Emma, you'd have to reproduce a staggeringly detailed configuration. Every atom in your body, their quantum states, and the entire history of incoming signals to your brain up to the exact second of now. Our observable cosmos is vast, but finite. The probability of that exact puzzle assembling somewhere inside it is essentially zero.
Okay, what about a similar Emma? Same look, similar personality.
That's not zero. Similar is far easier to reproduce than identical. Think two songs that sound almost the same. The melody is familiar, but the notes differ here and there. In a galaxy with trillions of worlds, a biologically similar civilization could arise, although it would still be extremely rare.
Now bring in your favorite word, multiverse.
Then the game changes. In eternal inflation-style multiverse models, there are effectively infinitely many bubble universes. With an infinite number of trials, even extremely unlikely events become guaranteed somewhere. So yes, somewhere out there could be an Emma who matches you bit for bit, possibly infinitely many.
So, can we swap funny memes through a space loophole?
Sadly, no communication. Those doubles lie outside our causal cone. It's like knowing there's an identical house somewhere on an infinite street, but there's no road to get there. Physics doesn't allow it.
What about Boltzmann brains? I've heard scary takes.
That's a thought experiment. In an infinitely old or large universe, random fluctuations might momentarily assemble a conscious brain with false memories. Mathematically possible, yes, but physically and observationally, we see no sign of that dominating reality. Cosmology is constructed so that normal observers, those who arise by the usual astrophysical and biological route, dominate. If your theory predicted Boltzmann brains everywhere, the theory would be suspect.
Sum it up in one human paragraph.
In our observable bubble, exact copies are almost certainly absent. Similar people are possible, but very rare. In an infinite multiverse, exact duplicates are guaranteed, but forever unreachable. Philosophically intriguing, practically useless.
So better to invest in the one and only original Emma right here, right now?
Absolutely. Uniqueness isn't metaphysical fluff, it's about these precise space-time coordinates. We get one shot to fill this slot with meaning.
Beautiful. What's next?
Next, we'll dig into geometry, why wormholes might connect different universes but don't act as simple teleports within ours, and how causality locks the door one way. Don't go anywhere and subscribe so you don't miss the next episode.
Nathan, straight up. A wormhole is a cheat code, right? Step into a closet here, pop out in Andromeda.
I wish it were that simple, but no. Think of a city with a closed highway. A wormhole is like a service tunnel that could shave off the trip, but it's gated by causality turnstiles.
Okay, what flips the turnstile open?
You'd need exotic matter with negative energy, basically an anti-ballast for the tunnel. We see tiny hints of this in nature, the Casimir effect. But that's microscopic. To make a traversable tunnel, you'd need a warehouse of those bricks. And where to source that warehouse is anyone's guess.
Why is causality such a killjoy? Why is the cosmos so fussy?
Causality is the universe's anti-paradox lock.
Give people a free teleport, and you can start calling the past and breaking stories, grandma paradoxes, lottery paradoxes, chaos. The universe protects the arrow of time like airport security. You step into a restricted zone and the alarm goes off.
But what about black holes and looping trajectories? Can't you sneak through there?
Black holes are the cosmos's industrial grinders. Sure, equations admit exotic solutions, but a real black hole is turbulent, scorching, radioactive, like a cement mixer that chews up everything. Coming back intact and leaving causality untouched? Practically impossible.
Bottom line for listeners, wormholes are elegant geometry, but without negative energy fuel, they're a closed door.
Exactly. Pretty on the chalkboard, stubborn in reality. We see hints of the building blocks, a matchbox, but what we need is a bridge.
Headline?
Space can cut the route, but it won't let you cut the pause.
Next up, we ask whether you can actually beat light speed via expanding space, clever tricks, or quantum loopholes, and why none of it gives a straight, reliable messaging line. Don't go anywhere, and subscribe to the podcast. The best part's coming.
Be honest. Can you outrun light, or is it like trying to outrun your own shadow?
Locally, no. Think of it as the universe's traffic law. The speed of light is the limit on any road. But the trick is, you can move the road itself. Like an airport moving walkway. You walk normally, while the floor beneath you carries you along.
So galaxies spread apart, not because anyone slammed the gas pedal, but because the road's surface is stretching.
Exactly. Cosmic expansion is the moving walkway. Local speed rules aren't broken, yet distances grow as if everything is driving away. That creates a horizon, regions receding faster than light can carry news.
What about building your own road, a warp bubble? Sounds like a business jet for star captains.
Beautiful dream. Huge maintenance bill. A stable warp bubble needs exotic energy with a negative sign, an anti-ballast, to stop it collapsing. Nature gives tiny hints, the Casimir effect. But that's crumbs. We'd need a warehouse.
Okay, no magic. What about wormholes? A shortcut through the storage yards of reality.
Geometrically, yes, like a service tunnel. But to be traversable, you again need exotic matter. And crucially, causality puts turnstiles at the entrance. If a tunnel permits skipping the time cue, paradoxes appear. The universe tends to mute such schemes, like airport security shutting a suspicious route.
Fine, pull out the rabbit. Quantum entanglement. Everything's linked instantly there, right?
Entanglement is like a synchronized orchestra backstage. Parts know about each other, but you can't slip a note to the audience instantly. There are correlations, but no faster-than-light signal.
And quantum tunneling? A particle pops through a wall? Maybe a ship could hop to Proxima?
Tunneling is about probabilities, not express delivery. For a ship, it's like trying to sneak through a mountain by flipping coins billions of times. Safety systems and vanishingly small odds make it impractical.
Then why do headlines say galaxies recede faster than light?
Because that's the rate at which distance grows, not the speed of an object moving along a road. Imagine dots on a stretchable rubber sheet. As you pull it, points separate faster than your pencil moves, though locally nothing breaks the rules.
So, bottom line, you can't outrun light, but you can cheat with the pavement, only the bill is exotic stuff and causality stays intact.
Exactly. The universe allows clever layouts of space, but doors that invite paradoxes remain locked. We can speed up, optimize paths, exploit useful trajectories, but we can't run the red light of physics.
Headline for listeners in their earbuds: light is the limit for engines, but sometimes the road itself moves.
Next, we'll talk about how to look for civilizations whose road already runs. Technosignatures, laser beacons, global night cameras for the sky, and why we need them. Don't go away and subscribe to the podcast. The best is ahead.
Is it true that Comet Borisov wasn't discovered by NASA, but by an amateur with a homemade telescope? That's like winning Wimbledon in your backyard.
Exactly. Gennady Borisov. Persistence, optics he built himself, and a sky he scanned every night. The result? ʻOumuamua 2019, the first textbook interstellar comet with heavy outgassing. Sometimes the big cosmos is found not by giant facilities, but by patient people.
How many of these tourists do we have so far?
Right now, there are 3 confirmed ones. ʻOumuamua 2017, dry and strange. Borisov 2019, the textbook comet. And 3I Atlas 2025, a distant water hydrant leaning towards CO2 with a couple of optical surprises. A solid trio for comparing other stars' kitchens.
Can we catch pieces of these visitors on Earth, like fishermen hauling a net?
People try. Teams hunt for micrometeorites and candidate interstellar fragments, magnetic trawls, sifting sediments, ocean expeditions, including near Papua New Guinea. The evidence is disputed, but the method is clear, like a metal detector on a beach, only the beach is the seafloor and the sky's ballistics.
And what did Borisov give us beyond pretty photos?
He told us that the recipes out there differ. ʻOumuamua, a thin chip with no tail. Borisov, a cold gas comet. Atlas, a CO2 kitchen that lit its water early. Simple conclusion. Comets ferry the ingredients for life across the galaxy, but each baker mixes a different dough.
So this isn't folklore anymore, it's 3 real calling cards from other systems.
Yes. The better we image them and sniff them with spectra, the more precisely we learn how life's ingredients are assembled and transported in the universe.
Next, we'll talk about how to tell natural calling cards from potential technosignatures, where to look for laser beacons, how to spot handmade features in tails, and why we'll need global all-sky night cameras. Don't go away and subscribe to the podcast.
Nathan, let's put it all on the table. SETI is about looking for aliens, and the Comet Kitchen is about figuring out what life's made of. Are these the same field?
Neighboring fields. Picture an airport. SETI listens to the PA system, radio signals, laser flashes. Comets are us entering the staff kitchen and checking the fridge. Water, CO2, CO, organics, dust. One asks who's speaking, the other asks what are they feeding.
Okay, the PA system, what exactly do we listen for so we don't confuse it with junk?
We hunt for narrow, steady tones, a thin whistle that drifts with Doppler and repeats. In optics, we chase ultra-short laser pulses, nanoseconds, like a perfect strobe click. Anything too neat and repeatable becomes a candidate.
Name the tools so people know who's on the job.
Radio, Greenbank, Meerkat, FAST, and programs like Breakthrough Listen. Optical or laser, big mirrors like Keck, VLT with nanosecond detectors, comets, JWST, Hubble, SphereX, coronagraphs, SOHO, stereo, GOES, survey telescopes, pan-stars, and the coming Vera Rubin LSST, a true all-sky night camera.
In the kitchen, how do we tell a comet's soup is relevant to life?
Comets are couriers of CHNOPS, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. We measure OH, water tracer, CO2, CO balance, organics like CN, dust grain sizes, and isotopes, DH, 12C over 13C. Lots of water plus the right organics means the building blocks for life are actively moving around that system.
Give me 3 quick flavors of interstellar guests to remember.
ʻOumuamua 2017, the dry chip. No tail, odd non-gravitational motion. 2I Borisov 2019, the classic stew. Lots of gas, textbook tail. 3I Atlas 2025, a CO2-rich kitchen with early water activity, anti-tail to tail, and optical oddities. 3 different recipes from different stellar disks.
How do we separate honest chemistry from a hint of engineering? What's the boundary?
Step 1. Explain everything with natural physics. Gas jets, icy grains, solar pressure, normal brightness phases.
Step 2, if something left is too tidy, a strict schedule of flashes, geometric features laid out by rule in a tail, non-gravitational acceleration without visible gas, or bizarre element ratios, then we ask uncomfortable questions and seek independent confirmation.
Top 3 false alarms for SETI?
RFI, our satellites, radars, even cell tech, instrumental harmonics and ghosts, atmospheric or ionospheric phenomena. Thicks, repeat from another site, another frequency, another instrument. No repeat, trash it.
And for a comet, what would be a true wow for chemistry?
A clear, model-matching evolution of volatiles like Atlas, rare isotopic signatures that fit delivery models for water or organics, that turns pretty photos into practical cosmochemistry.
SETI looks for the voice, comets hand us the menu. Together, they map the universe's address and its diet.
Next up, Technosignatures in transits. How to tell a natural planet from an astro-engineered structure by the way a star flickers, which patterns look suspiciously right, and how to test them. Don't go away and subscribe. It's gonna get hot.
Nathan, plain talk. How do you tell from a star's flicker that what passed in front of it wasn't a planet, but someone's construction?
Look at the light curve like a star's ECG. A planet makes a smooth dip, gradual ingress, flat bottom, gradual egress. An engineered object gives a ragged silhouette. Steps, sharp edges, asymmetry, sometimes different depths each time.
So if the eclipse looks like Venetian blinds, that's a red flag.
Exactly. Picture a curtain made of segments. One slat gives a small dip, then a wider gap gives a deeper dip, then it narrows again. That's the signature of a swarm of modules or a torn geometry, not a smooth sphere.
And periodicity? Planets keep a schedule.
Right. A planet is like a commuter train on time. A megastructure can have a wobbly timetable, transit depth, duration, and shape change, and extra mini-dips appear as accompanying panels orbit nearby.
What else beyond transit shape gives away handmade work?
2 big markers. Infrared excess, like a thermal signature, like a night air conditioner running, and color dependence, transit depth changing across wavelengths in ways dust or atmospheres don't. Also, watch for sharp edges in the light curve and odd phases of reflected light.
Stars are noisy, though. Spots, pulsations, comets, hot Jupiters. How do we avoid false positives?
Work a natural checklist first. Spots or pulsations, check rotation and stability. Dust or comets, expect wavelength dependence and tail asymmetry. Rings or moons, these give regular signatures. If what's left is irregular but unnervingly orderly, raise the candidate flag.
Which instruments are on the job for these tricks?
Kepler set the bar. TESS scans the whole sky now. We use ground networks for cadence and big IR-capable telescopes and space observatories for thermal follow-up. Pro tip, multiband photometry in one night kills half the false alarms.
If it's a Dyson swarm, not a solid shell, what do we expect?
A scatter of small light bites that vary transit to transit, a persistent slight dimming of the star, and a warm IR background, like someone turned down the star's brightness with a dimmer while a flock of panels flew by.
And when a suspicious transit turns out to be just dust?
Dust is a master of disguise. The rule, multicolor light curves, plus dust spectrum, plus repeatability. If the mask slips, natural cause. If it holds, keep digging, but no trumpet blast until independent confirmation.
What about hot Jupiters pretending to be something else?
Check radial velocities, is the star tugged by a massive body, phase curves, and the secondary eclipse when the object hides behind the star. If mass and heat match a gas giant, it's a planet, not a megastructure.
What's the
gold standard proof?
A combo. Unusual transits in multiple bands, IR excess, no natural explanation after thorough checks, and ideally another technosignature, radio or laser, from the same system. One clue hints, three clues make a case.
Headline for commuters?
Planets cast round shadows. Engineering cast shadows with edges and a thermal whisper.
Next episode, building an all-sky night watch, continuous cameras, distributed telescopes, and what 24/7 monitoring buys us for catching rare signals. Don't go anywhere and subscribe. It's getting hot. Nathan, back to that odd object from Archipov's papers. It's like a planet, but not a planet. Is this a cosmic masquerade?
More of a guess by the shadow puzzle. A normal planet casts a smooth, round shadow, gradual ingress, a flat bottom, gradual egress. This one's angular, stepped, and changes from transit to transit, as if a row of Venetian blinds, not a sphere, drove by the star.
Okay, the shadow is weird, but stars themselves are messy. Spots, flares, dust. How do we know it isn't dirt on the lens?
We approach it like an investigator with a notebook. Step 1. Star spots. They produce sinusoidal signals tied to rotation. If it doesn't match, cross that off. Step 2. Dust and comet tails. Dust causes a wavelength-dependent dip. It colors the transit, and a slanted profile with a long tail. Step 3. Rings and moons. Those produce repeatable signatures. If after all that, the light curve still looks like drawn with a ruler, interest rises.
Paint a simpler picture. If it's a swarm of panels around the star, what will our telescope see?
Three things at once. 1. A scatter of tiny nibbles in the light curve whose depths and shapes drift from transit to transit. 2. A slight persistent dimming of the baseline, like someone flipped a dimmer. And 3. An infrared excess, a warm whisper. Some stellar energy is being re-radiated as heat.
Sounds cinematic. But what would kill the elegant hypothesis in 1 second?
The classic spoiler. A hot Jupiter. We check radial velocities, the star's wobble from the planet's mass, catch the secondary eclipse when the planet hides behind the star, and build the thermal phase curve. If everything matches a gas giant, it's a gas giant, and our panels get retired.
Do dust imposters ever look convincing enough to warrant a press release?
All the time. Dust is a master of disguise. The cure is simultaneous multiband photometry in a single transit. If the transit depth strongly depends on color, it's dust. And follow for months. Dust shapes evolve differently than engineered modules.
What instruments can realistically record such a fine ECG of a star?
Photometry. Kepler set the standard. TESS sweeps the sky now. Ground networks fill in cadence. Thermal, large IR telescopes, and space observatories, JWST class. The trick is simultaneous multiband coverage during one transit. That knocks down half the false positives.
If it's not a Dyson shell but a swarm, is that logistically plausible?
A swarm is more realistic than a solid shell. You don't need full coverage. A small optical depth with the right distribution can produce an irregular shadow and an IR signature. Picture a swarm of drones around a spotlight. Light dims in steps, and the air warms.
If it's not a Dyson shell but a swarm, is that logistically plausible?
A swarm is more realistic than a solid shell. You don't need full coverage. A small optical depth with the right distribution can produce an irregular shadow and an IR signature. Picture a swarm of drones around a spotlight. Light dims in steps, and the air warms.
What would be the gold standard proof that lets you pop the champagne?
A combo strike. Unusual transits seen simultaneously in multiple filters. Persistent IR excess not explained by dust. Negative tests ruling out natural causes, spots, dust, rings, moons, ellipsoidal effects. and ideally, another technosignature from the same system, a narrow radio line or optical pulses. One clue is a hint, 3 clues make a case.
Give listeners a headline they'll remember tomorrow.
Planets cast round shadows. Engineering casts shadows with edges and a warm trail.
Next up, how to build all-sky night eyes, distributed telescopes, 24/7 monitoring, and why we need our own space CCTV for rare signals. Don't go away and subscribe. The best is ahead.
Nathan, give it to me straight. If aliens are sending a hello, how do we catch it? Radio, lasers, drumming in a vacuum?
2 main channels. Radio, hunting for a narrowband needle, a pure tone, like a single perfect piano key. Optics, hunting for ultra-short laser pulses, measured in nanoseconds. A strobe you can see across half a galaxy if it's aimed right.
Quick history, useful and short.
Start the 1960s. Project Ozma. A small dish listening to a couple nearby stars at the hydrogen line, 1.42 gigahertz. Since then, dozens of programs. Today, we work with networks, Green Bank, Meerkat, FAST, and smart receivers that record spectra at very high resolution.
What's a narrow-band needle scientifically, but in plain English?
It's when almost all the signal's energy is squeezed into an ultra-thin slice, maybe a few hertz or less. Nature rarely does that. It prefers wide, noisy spectra. A needle in the noise stands out as an artificial transmitter.
Okay, how do you tell a needle from our own Wi-Fi floating in space?
3 filters. Doppler drift. The tone slides because the source moves or rotates. Earthly RFI usually sits still. Repeatability. Point the telescope away and it's gone. Point back and it returns. Coincidence. 2 telescopes at different sites see the same thing.
Optical lasers aren't a flashlight you stumble on. How do you catch them?
With fast photon traps, detectors that register nanosecond blips. We apply wavelength filters, look for repeat patterns, and require multi-pixel coincidences so a single cosmic ray hitting 1 pixel doesn't fool us.
What scanning strategy is currently in vogue? All sky or targeted addresses?
Both. Wide surveys so we don't miss a beacon to everyone. Targeted observations of nearby sun-like stars and habitable zone exoplanets. We also use smart tactics, listen near hydrogen hydroxyl lines, the so-called water hole, and scan for drifting frequencies. Maybe they purposely wiggle to stand out.
Translate the jargon. What's de-dispersion and why do we need it?
When a pulse crosses interstellar plasma, high frequencies arrive before low ones. The pulse gets smeared. De-dispersion reconstructs the original short pulse, folding the sweep back together. Without it, the pulse is lost in the mush.
How many channels do you actually record? That must be tons of data.
Thousands to millions of narrow channels at once with Hertz-level frequency sampling and millisecond or sub-millisecond timing. It's big data from space, machine learning, pattern matching, cross-checks. Otherwise, you drown.
If they send a digital packet instead of a single beep, what then?
We look for modulation, clear rhythms, blocks in the spectrum, repeating structure. Then we try to extract a simple code, binary patterns, prime numbers, geometric sequences, but first, statistics, then celebration.
Give me the red flag checklist for saying, hold up, this might be it.
It's a narrow, stable line with realistic Doppler drift, repeatability on multiple pointings, no local sources at the same time or frequency, ideally a multi-band or multimodal footprint, radio plus optical. The more of these are true, the stronger the candidate.
Why is the search still so hard with all our giant telescopes?
It's about time and geometry. A beacon can be highly directional and rarely sweep across Earth. If it scans, we catch a brief flash. Add terrestrial interference and the sheer sky volume, and you get cosmic Where's Waldo.
Headline for listeners?
We hunt a solo needle in a chorus of noise. In radio, a thin squeak. In optics, a strobe click. We check 3 times. A handshake only after independent eyes confirm.
Next up, we'll talk about strange finds, the famous wow signal, puzzling repeats near the hydrogen line, and why some miracles evaporate under scrutiny while others stick around for years. Don't go away and subscribe to the podcast. That's where it gets most intriguing.
Nathan, light the campfire of stories. Tell us about the legendary wow. Was that a cosmic hello or just the universe sneezing?
More like the cosmos cracked the door and slammed it shut. Summer 1977. The Big Ear radio telescope catches an almost perfect narrow note on the hydrogen line, holds for 72 seconds while the beam scans. The operator circles it on the printout and writes in huge letters, "Wow!" And silence. No encore.
Ugh, that's painful. Like spotting a UFO on the subway and having the camera show 1 pixel and a black cat.
Exactly. The parameters were beautiful, narrow band, plausible Doppler, but there's no repeat. For science, it's a legendary candidate. You hang it on the wall, but you don't put it in the textbook.
Okay, next phantom of the airwaves. You mentioned 3 pulses in 2003 near the hydrogen line. Was that Morse for we're here?
More like, we're here, maybe. 3 narrow needles near 1.42 gigahertz. All the hallmarks we like, but the drift was jittery, we repointed, and the field was empty. Conclusion? Intriguing, not conclusive. The cosmos winked and ran off.
Why are they so shy? Are we bad listeners, or do they whisper once a century?
Both. Imagine a scanning spotlight. The beam is thin, and Earth only gets hit for seconds. Add our radio mess, like satellites, radars, like a neighbor with a jackhammer. Modern tactics are wider coverage, faster sampling, and more independent ears.
Remind me about the water hole. Sounds like a poetic bar scientist's visit.
True. It's essentially a quiet spectral bar between the hydrogen and hydroxyl lines, low natural noise, and a wink at H2O. If you want to be heard by many, whisper there.
Okay, give a human checklist. When do we say, that might be it?
4 nails for the poster. A narrow, stable line with realistic Doppler drift, not local RFI. Repeat on request, point, see it again. Coincidence, 2 independent telescopes see the same thing. And clean Earth check, ruled out satellites and radars. Bonus, an optical pulse from the same spot and time, then you can cool the champagne.
So, wow alone isn't enough. We need wow, wow, wow with signatures and stamps.
Yes. Space likes reprises, we like protocols. A beautiful single flash is romance. Repeats turn romance into science.
And for folks listening on their commute, what does wow teach us?
Patience and discipline. Catch the needle, but verify 3 times, call your neighbors, shut off the home routers, and only then clap. Next, we'll cover how not to drown in fakes and interference, the inferno of RFI, how de-dispersion compresses stretched pulses, and where machine learning helps when the needles number in the billions. Don't go away and subscribe. The best is coming.
Nathan, be straight. Is the Drake equation a real alien calculator or just a pretty counting rhyme for romantics?
Both. Think of it as a salad recipe. Stars, planets, warm kitchens for life, the fraction where life actually lights up, the fraction that learns to talk, and the crucial last ingredient, how long the restaurant stays open for visitors.
So you can chop a ton of ingredients, but if the kitchen closes after 5 minutes, nobody gets fed.
Exactly. The final multiplier, L, is how long a civilization stays open. If a diner is open for only 100 years in a 10 billion year galactic day, your odds of walking in are tiny.
Give it to me without formulas so a cabbie gets it.
Okay, Suppose there are tens of billions of potentially Earth-like worlds. Even if life sparks rarely, across time there could be hundreds of thousands of intelligent starts. But if each one talks on the air for only a century, the number online right now is maybe single digits across the whole galaxy, like a huge city with only a couple of 24-hour pharmacies.
Harsh. So maybe there are many, but we're lonely by schedule?
Bingo! The problem isn't nobody exists, it's that communication windows don't overlap. We've been broadcasting at high power for just a little more than a century, a firecracker, not a lighthouse.
That technological burst idea, a firework?
Yes, fireworks are bright and short. To boost L, a civilization must become a lighthouse, steady, long-lived, and not burning out its batteries.
How do you live longer as a civilization, practically?
3 steps. Don't self-destroy, avoid catastrophic war or systemic collapse. Stabilize planetary conditions, keep your thermostat in the green, and live within means. Manage energy, resources, and waste sustainably instead of flooring the accelerator.
Will the equation stop stinging our eyes?
If L grows from 10 years to 10,000 years, the cosmic chatter flips from whispers to a marketplace hum. Longer lifetimes are the volume knob for the whole equation.
So, what do listeners take to work tomorrow?
We're not necessarily alone, we're just out of sync in time.
Next, we'll talk about why our technological burst may already be fading, what slowing growth curves look like, and what that implies for our L. Don't go away and subscribe. This is important.
Nathan, everyone yells, technological boom. But you whisper, the boom is already losing steam. Is that real or just nostalgia for film cameras and warm radio?
It's real. Picture a soda bottle. Fizz spills over. That's us for the last 100 years. After that, the bubbles settle. Tech follows an S-curve. Fast surge, then a plateau. A new normal.
What exactly is settling? Give people examples so they actually nod instead of snooze.
3 lines on the dashboard. Population growth rates are falling. Some countries are already shrinking. GDP per capita still grows, but not like the explosive 1950-1970 decades. Energy, we use more, but there's no free infinite socket. Infrastructure and physics impose limits.
But gadgets get smarter. AIs draw cat pictures. Isn't that a fresh boom?
That's refinement inside an existing platform, not a new floor. It's like adding a spoiler to a car. It looks cooler, but the speed limit hasn't changed. Improvements continue, but materials, logistics, and energy eventually hit atomic and geographic limits.
Why does growth bend? Did we get wiser and decide to slow down?
No, it's the law of large numbers. The easy wins are already taken. Electricity, vaccines, basic connectivity. Next gains cost more and are harder. It's like running on a Red Queen treadmill. To stay where you are, you must run. To actually advance, you need a new level, not just software tweaks.
So, a technological civilization is a short flare?
The super bright burst tends to be short. Most civilizations, if they exist, either never reach that burst or hit a plateau quickly. That's why few are shouting on the air. The firework is brief, making our Drake equation L narrow.
That sounds bleak. How do we avoid being a one-day wonder?
Switch from sprint mode to marathon mode. Build energy foundations, nuclear, fusion, renewables with storage, not gadgets, baseline power. Close cycles, recycle materials, close water loops. Increase resilience, eliminate single points of failure, decentralize. Change KPIs from faster, cheaper to longer, stabler.
Translate that to kitchen terms. How to test we're on the right track.
In 50 years, if we have cleaner air, fewer big accidents, cheaper baseline energy, And steady, non-spiky progress, we've turned a firework into a lighthouse.
And this actually raises our L, the time we're on the line for neighbors?
Exactly. Longer life equals longer broadcast. The longer we shine without self-destructing, the higher the chance someone answers.
Headline for listeners?
Fireworks impress. Lighthouses endure. Balance energy, close cycles, stretch your lifetime, and the universe's conversation gets louder.
Next, we'll discuss how to spot other civilizations from their future economies, the Kardashev scale, what first and second type habitats look like, and the footprints left by societies that became lighthouses instead of fireworks. Don't go away and subscribe, it gets even better.
If civilizations are like cities, can we gauge their size by their power bill? Like picking at their cosmic utility receipt?
That's exactly the idea behind the Kardashev scale. Type 1 controls all planetary energy sources, wind, sun, core, like managing Earth's entire power grid. Type 2 taps directly into its star as if building a giant solar farm around it. Type 3 runs an entire galaxy, like one operator managing every city on Earth from a single dashboard.
So we're a string of fairy lights on a balcony?
Pretty much. We're around 0.7. We've got smart bulbs, but we're far from flipping Earth's master switch. And the stellar socket, that's a moonwalk away. Literally.
Okay, but how do we find these types? There's no neon sign in the sky saying, Type 2, discounts on Tuesdays.
We look for waste heat, like using a thermal camera on a city at night. If someone's milking a star, the system might look slightly dimmer in visible light, but warmer in infrared. It's like pulling down the blinds, less light, and turning on a heater, more warmth.
But dust around a star also glows in IR. How do we not confuse a panel swarm with a sandstorm?
Dust is like a wool sweater. Its spectrum shows patterned threads, distinct lines. Tech heat is smooth, black body-like, no patterns. Plus, engineered systems often cause irregular transits, shadows with edges, like blinds, not round like planets.
Can we even spot a Type 1 from afar? That's just household management.
Barely. It's like trying to hear one apartment in a noisy building. We infer it from stable climate, clean atmospheric spectra, and lack of smokestacks. The signal isn't loud, it's precise.
And Type 3, that's vaguest across the galaxy.
If it existed loudly, we'd see infrared-coated galaxies, too warm and oddly dim in visible light. We haven't found any obvious ones, so if they're out there, they're either subtle, cold, or hiding better than we imagine.
What Batman tools help us hunt?
Wide IR surveys to catch excess heat, long-term monitoring of light curves for odd shadows, cross-checking radio and laser clues. Algorithms look for two neat patterns and infrared excesses that dust can't explain.
And why do we need this scale, beyond curiosity?
It's a growth ruler. It reminds us, don't just shout louder, shine longer and cleaner. Type 1 is a planetary lighthouse. Type 2, a stellar beacon. If we're ever heard across the stars, it'll be because we lasted, not because we cranked the amp to 11.
Next, we'll explore why Type 1 civilizations are nearly invisible to current searches, where their signals hide, and how to build 24/7 night eyes for the sky to catch both beacons and warm whispers. Don't go away and subscribe to the podcast. The best is ahead.
Nathan, give it to me straight. What's her actual strategy? Is it more like fishing with a net or a rod?
Both. In radio, it's a net, wide sky surveys. In optics and narrow bands, it's a rod, targeted shots at nearby stars. But the core principle is the same. We're looking for beacons, not random whispers.
Why beacons? Wouldn't a normal civilization just say hi quietly and politely?
Because physics is a strict accountant. A beacon is visible to everyone all the time. A whisper, only if you're close and lucky. It's like a lighthouse at sea versus a flashlight on the beach.
But a lighthouse burns serious power. Can a Type 1 civilization even afford that?
Exactly. No. Planetary civilizations, Type 1, can't afford to shine in all directions all the time. That's why early searches defaulted to looking for Type 2, those already plugged into their star.
So our method is biased. We look where it's bright and rich and risk missing the quiet ones.
Spot on. Classic SETI focuses on narrowband radio lines and nanosecond optical pulses, logical for powerful transmitters. The trade-off? False negatives for the quiet civilizations.
Paint me a picture. What's the practical difference between radio and optical?
Radio, we search for a thin needle in the spectrum, stable frequency, decent Doppler drift, repeatable. Optics, we hunt for ultra-short strobe flashes, like a laser ping from a stadium. Radio is listening to a choir. Optics is spotting a camera flash.
And what about Type 1? If they can't run a spotlight, how could they show up?
Scanning beacons, a beam sweeping the sky, rare targeted pings, timed campaigns like when we're near a planetary transit, plus indirect technosignatures, weird transits, warm IR traces, patterns too clean for nature.
So the ideal method isn't one super ear on a megascope, but an orchestra of instruments?
Exactly. Wide radio surveys, plus fast optical traps, plus long IR monitoring for heat trails. And crucially, coincidences. Multiple sites observing at once to rule out earthly interference.
And timing? The universe won't wait for us to reboot the software.
We need 24/7 mode. Think citywide camera grid. Cheap, distributed, watching the whole sky. Smart algorithms flag events. Big observatories swoop in to confirm.
So the old eternal beacon approach is convenient but narrow. The new one is catch rare flashes, then lock them down.
Exactly. The old method was high beams. The new one is night vision plus walkie-talkie. We catch more faint, fleeting events and call in backup instantly.
Okay, final thought. For the folks listening on the bus, we're no longer waiting for a lone spotlight. We're building a trap network for 1,000 tiny lights.
Next up, why every civilization, from Type 1 to Type 2, eventually hits an evolutionary singularity, how that changes its voice, and what traces are left behind when a firework becomes a lighthouse. Don't go away and subscribe to the podcast. It's about to heat up.
Nathan, let's keep it strict. What do you mean by evolutionary singularity?
A brief period of accelerated technological and social transformation, typically spanning a few centuries, during which a civilization dramatically increases its productivity, energy capacity, communication speed, and knowledge volume.
Does this apply across Kardashev types?
Yes, Type 1 civilizations focus on managing planetary resources and climate. Type 2 civilizations handle energy distribution and utilization at the scale of a stellar system. In both cases, the goal is the same: transition from exponential growth to controlled, sustainable dynamics.
What observable signs mark this transition?
Reduction of inefficient energy losses, stabilization of the energy profile, including infrared emissions, decline in random or unstructured radioactivity, shift toward targeted, infrequent communications, increase in closed-loop material cycles and energy storage systems.
What tends to become the bottleneck?
Growth rates, system manageability, and long-term predictability. This demands robust feedback loops, failure mode scenarios, redundancy in critical infrastructure, and standardized safety protocols.
How does this affect our search strategy?
We should expect two signal classes. from young civilizations, short, irregular, energy-intensive transmissions, and from mature ones, rare, highly directional signals with dense information and minimal leakage. Hence the strategy: wide panoramic surveys for bursts, plus long-duration infrared monitoring to detect stable thermal traces of infrastructure.
What are the practical priorities for us?
Increase the share of clean baseline power sources, expand energy storage capacity, transition to recycling loops, build resilient networks, and shift tech KPIs from short-term metrics to long-term ones: reliability, longevity, and stability.
And finally, what does this mean for the Drake equation?
Extending the L parameter, the duration of detectability, through sustainability dramatically increases the odds of temporal overlap with other civilizations.
Next, we'll talk about funding and search efficiency, who pays, how telescope time is allocated, and which projects actually improve our chances of catching rare signals. Don't go away and subscribe to the podcast.
Nathan, who's footing the bill for this cosmic eavesdropping? And what do we get besides shiny press releases?
Major private investments and national observatories. The flagship example is the $100 million Breakthrough Listen program. Telescope time on major radio arrays, upgraded receivers, cloud infrastructure, and open data archives. Plus, government-backed hours on radio, optical, and infrared instruments through joint proposals.
Okay, but does the power bill pay off? Have we found anything you can actually put on the table?
No confirmed technosignals yet, but we've massively improved sensitivity, bandwidth, frequency scanning speed, and, most importantly, upper bounds. We now know what's not visible within N stars at given thresholds. Plus side benefits: billions of spectra for astrophysics, transient catalogs, and new RFI mitigation techniques.
How do we know the money's being spent wisely? We need metrics, not mantras.
Clear KPIs: sky time, sky coverage times observation time, star hours in the water hole and nearby bands, sensitivity threshold, watts per hertz at distance x plus frequency range, candidate verification speed and false positive rate, coincidences, how many events were confirmed by independent sites, and open data share and reproducible pipelines.
Where's the bottleneck right now? Telescopes, software, or people?
All three. Instruments: we need wide-field, fast, low-cost setups, radio arrays, and nanosecond optical traps. Software: better signal extraction amidst RFI and real-time de-dispersion. People: stable funding for teams that monitor 24/7 and can rapidly follow up on candidates.
Say I've got a $10 million annual check. Where do I place my bets?
Balanced portfolio: commensal observations, piggyback on existing telescopes for max star hours per dollar, distributed fast optics networks, catch rare flashes, multi-site radio coincidences, instant candidate verification, open pipelines and ML grants, fewer false alarms, faster review, and targeted campaigns, focus on nearby sun-like stars and confirmed transiting exoplanets.
And the honest bottom line?
We're not buying a guaranteed signal. We're buying the chance not to miss one. In recent years, we've widened the window. If someone's shouting at detectable levels, we'll catch it or clearly show where we're still blind.
Next, we'll explore how quiet Type 1 civilizations might still send a signal, from scanning beacons to thermal hints in infrared. Don't go away and subscribe to the podcast. The tastiest bits are just ahead.
So Nathan, the million-dollar question. If a civilization is still planetary, Type 1, how could it possibly reveal itself? No stellar sockets, no galaxy-wide floodlights.
Three main clues. 1. Rare but intentional pings, tightly focused radio or laser pulses sent on a schedule, brief, precise, and in quiet spectral zones. 2. Scanning beacons. A beam slowly sweeps the sky. Earth lands in the spotlight for seconds or minutes. 3. Indirect technosignatures. System behaviors that nature struggles to mimic. Atypical transits, a too clean patterns, or a small but persistent infrared excess.
Translate intentional ping into a checklist for observers.
We're looking for a narrow line, Hertz level or tighter, realistic Doppler drift, the source is rotating or moving, repeatability on repointing, ideally a coincidence across two observatories and an optical counterpart at the same second. One frame isn't enough. We build a case.
So, scanning beacons, timing is everything?
Exactly. You need 24/7 coverage and wide ears, distributed radio arrays, and optical traps for nanosecond flashes. Algorithms catch rare spikes and immediately alert the heavy artillery for confirmation.
What counts as too clean in indirect signs?
For example, non-standard transits, shadows with angles, steps, or shifting geometry. Also, a modest IR excess that can't be explained by dust, no spectral lines, and temporal stability. Nature loves rough edges. Engineering prefers clean lines.
So how does a Type 1 save energy but still reach us?
With precision. A ping during a transit window, when their planet aligns with ours, use of the water hole between H and OH lines, and short, high-density packets, easy to spot, cheap to send.
And what do we need to build or buy to avoid missing these quiet ones?
Multiple layers of detection, commensal modes on big telescopes, listen while they do other science, low-cost, wide-field networks, radio and optical, with auto-triggers, multi-site coincidences by default, and open pipelines and archives so the world can recheck candidates.
And a quick takeaway for those who just heard this at a red light?
Type 1 doesn't shout, it winks. To catch the wink, you need long shifts, wide eyes, and fast hands for confirmation.
Nathan, let's keep going. If someone sends a laser hello, how do we actually catch it? It's not a flashlight.
We use fast photodetectors mounted on telescopes. The classics, PMTs, photomultiplier tubes, and SPADs, single photon avalanche diodes. Advanced level, SNPDs, superconducting detectors with picosecond timing. The goal is to spot a nanosecond pulse and separate it from noise.
So, what's the observation setup? One sensor and a prayer?
Not quite. At least 2 or 3 coincidence channels to filter out random flashes, cosmic rays, sparks, electrical noise. In front, narrow band filters to cut background and apertures to reduce sky glow and nearby star interference.
What wavelengths are we listening in?
Mainly visible and near-infrared, roughly 400 to 1700 nanometers. These bands are more transparent in Earth's atmosphere and match common laser tech. We use multiple filters. If a pulse shows up in 2 bands at once, that's a strong clue.
What's the shutter speed we need?
Nanosecond or faster. We operate in single photon counting mode, detect individual photons, and build up statistics. A trigger happens when an anomalously high number of photons hits multiple channels in a very short window.
Sounds like a false alarm factory. What about calibration?
Essential. Dark frames and sky background for each filter, pulse calibrators, picosecond LEDs or lasers, time sync, GPS or PTP, without it, coincidences are meaningless, flat fielding so pixels don't lie.
And does the atmosphere mess things up?
It adds background and twinkle, but a nanosecond pulse is shorter than atmospheric turbulence. It won't smear. Key is dry, dark sites and a good visible zenith. Satellites and planes, we tag them with trackers and mask them using ephemerides.
How do we know it's a deliberate signal, not, whoa, a meteor?
Checklist. 1. Channel coincidence within one observatory. 2. Multi-site coincidence, the same millisecond across telescopes. 3. Repeatability when pointing at the same star. 4. Spectral signature consistent in 1 or 2 narrow bands. Ideally, a rhythm, e.g. a periodic packet.
Do we need a giant mirror, or is fast better than big?
Better to have a medium telescope plus ultra-fast detector with a wide field. Even better, a network of mediums, more sky coverage, and better coincidence detection. Big scopes come in for candidate confirmation.
Scanning strategy. Whole sky or top start list?
Combo. Whole sky, cheap, wide-field nanosecond traps. Targeted, nearby sun-like stars and confirmed transiting exoplanets. Transit moments are ideal ping windows.
And finally, what goes in the archive so others can verify?
Raw Poton time series, filter metadata, precise timestamp, coordinates, weather data, satellite or aircraft mask logs, and the pipeline source code. Without that, any ping is just a story.
Perfect. Next, we'll talk about why radio is harder than it looks, array sizes, the computational grind of millions of channels, and the cost of missing a single peak that could have been a hello. Don't go away and subscribe to the podcast. The best is ahead.
Nathan, be honest, why is radio such a pain? We've got dishes, antennas. What's the bottleneck?
3 big rocks: size, noise, and computing. To hear a distant, narrowband signal, you need a massive collecting area and long integration. That means arrays with thousands of elements and kilometer-scale baselines. Earth is flooded with RFI, satellites, radars, 5G. Our air hums louder than space. Millions of narrow channels times millisecond slices equals data streams in terabytes per second. You can't just record and think later. You have to process in real time.
Okay, details. Why doesn't one big dish solve it?
A single dish gives sensitivity but has a narrow field and poor localization. An array, via phasing, forms dozens of electronic beams at once, scans wider, and pins down coordinates. Downside? A monstrous load of correlations and calibrations.
Calibration, like mixing a music track.
Exactly. Each antenna has its own phase shift, gain, noise temperature, plus the ionosphere jellifies the phase. Without constant calibration, the beam blurs and false positives explode.
RFI, is it just subtract known frequencies?
If only. You need satellite ephemeris masks, statistical detectors for too-perfect stability, polarization analysis, and most importantly, coincidence. A second site must see the same thing. Local interference won't repeat there.
Computing, what's the heavy lift?
In parallel, you must split the band into millions of narrow channels, search for narrow peaks and Doppler drift, perform de-dispersion, incoherent/coherent, in real time, and decide what to retarget immediately for confirmation. This takes a GPU/FPGA grid, not a desktop under the table.
Why does everyone want baseband saved?
Baseband is the raw complex stream before detection. If a candidate pops, you save a few seconds back, ring buffer, and reanalyze with any method. Without baseband, the signal versus noise debate is often unresolvable.
So, wider or deeper is a constant trade-off.
Yes, wider equals more sky, better odds of catching rare bursts, but lower sensitivity. Deeper equals fewer targets, but lower detection threshold. The sweet spot is commensal modes, listen while doing other science, and distributed networks to cover both width and depth.
And today's #1 bottleneck.
Not hardware alone, the whole system. Synchronized multi-site observations, real-time de-dispersion and drift tracking, auto-triggers for retargeting, and open pipelines for fast rechecking. If any link breaks, we lose rare signals.
Final thought for listeners. No despair?
Radio is hard and expensive, but scalable. Add antennas, speed up software, and the window widens. We're not deaf, we're still building the right ears.
Next, we'll talk about the optical channel over long distances, why lasers can reach hundreds of thousands of light years, what power levels are realistic, and how to build traps for the whole sky. Don't go away and subscribe to the podcast. The next part is coming in hot. Nathan, we've covered radio, but what about lasers? Is that even real or just sci-fi with a neon sign saying, "Hello, Earthlings"?
It's real. Short optical pulses can be visible across hundreds of thousands of light years. The secret is simple: a narrow beam, massive peak power, and minimal chatter between flashes.
What does narrow beam mean in grown-up terms?
It's set by diffraction. The larger the emitter's aperture, the tighter the beam divergence. A big mirror means a more focused stream of photons, less loss, less background at the receiver.
What kind of power do you need to be seen beyond the nearest neighbors?
Think inertial confinement fusion levels, like lasers used at NIF. You get gigantic peak power in a very short pulse. A sub-nanosecond poke like that can be caught even by small telescopes with fast detectors.
Why short pulses? Isn't long and bright better?
Long is expensive and blends into background. A short pulse gives insane contrast. In 1 nanosecond, you get an anomalous photon spike, which is perfect for coincidence detection.
And aiming. That's like hitting a coin with a laser pointer across the ocean.
Exactly. You need ultra-precise astrogation and target motion prediction. That's why it's smarter to ping during transit windows. When we pass in front of our star, the address and timing are known.
What light frequencies work best for these greetings?
Visible and near-infrared, roughly 400 to 1700 nanometers. Atmospheric windows for receivers, and mature tech for transmitters. You can also use narrow filters to stand out from background glow.
How big does the lamp need to be on our end?
Not giants. What matters is fast detectors, PMT, SPAD, SNSPD, and channel coincidence. A network of medium telescopes watching 24/7 beats one giant that's busy with galaxies.
Does optics beat radio for range?
Not beats, it complements. A laser is a narrow spotlight with phenomenal information density. Radio is a broadband ear that punches through plasma. The ideal strategy is to search both.
Won't the atmosphere kill the pulse?
The pulse is too short to smear. The real issue is background and clouds. Solution? Dark sites, filters, dual observatory coincidences, and precise time sync.
So on the sender side, it's all about mirror, power, and aim.
And repeatability. A pinging calendar, predictable frequency, maybe even a code like primes or rhythm. That's how the receiver knows this isn't a meteor or satellite, it's intentional.
Okay, this doesn't sound like magic. It sounds like engineering.
Exactly. Big aperture equals tight beam. Short, powerful pulse equals high visibility. Right window and rhythm equals recognizability.
And for us Earthlings, what's the receiving recipe?
A network of medium telescopes with fast photodetectors, narrow filters, coincidence detection across channels and sites, instant recording of raw time series, and an open archive.
Next, we'll talk about laser phased arrays, how to stack hundreds of small beams into one ultra-precise signal, and why that's key for future interstellar communication. Don't go away and subscribe to the podcast. It's about to get even denser.
Nathan, this sounds like Jedi tech. What exactly is a laser phased array, minus the magic?
It's a grid of small lasers working together as one large, highly precise beam. We synchronize their phases in time so the waves add up in a chosen direction, creating a steerable narrow beam without needing a single giant mirror.
Why is that better than one super laser?
Scalability and flexibility. You can expand the array in modules, shut off faulty elements, retarget the beam electronically, no moving parts, and even form multiple beams at once, like a multi-head spotlight.
Okay, where's the tricky part?
3 main challenges: phase and timing, synchronization down to picoseconds, or the beam blurs. Heat and stability. Lasers heat up, frequencies drift, so active stabilization is a must. And optics and atmosphere. On Earth, you need adaptive optics or to work through atmospheric windows. Best to place nodes high and dry or move them to space.
So space makes it easier?
Easier for atmosphere, harder for power and cooling. But a space-based array offers perfect transmission and keeps the beam tight over interstellar distances.
What about combining beams from multiple ground sites? Is that even possible?
It is, if you have reference beacons, ultra-precise time sync, optical plus GPS-like systems, and low-latency links. It's more like transmission interferometry. Tough engineering, but conceptually feasible.
Sounds like a tool for planet-to-planet messaging. Why does SETI care?
2 reasons. Transmission, send narrow, energy-efficient signals into specific windows, like during a planet's transit. And signature, embed artificial geometry in the signal, like multiple synchronized beams with fixed delays. Nature rarely does that.
Are we testing mini versions already?
We are. Prototypes of optical phased arrays exist for communications and LiDAR. Still Earth-scale, but the principles are the same. Phasing, calibration, and electronic beam steering.
How do we detect this as observers?
Look for nanosecond packets with stable intervals and unusual spatial structure, like multiple close sources marching in formation. In the spectrum, narrow needles synchronized across 2 or 3 bands. Critical, coincidences between observatories and recording of raw time series.
Wrap it in one sentence.
Laser arrays let civilization speak far, clearly, and efficiently, and give us a chance to spot artificial precision that nature rarely mimics.
Next, we'll explore how to build all-sky traps, networks of low-cost optical stations, time synchronization, and what counts as the gold standard of confirmation. Don't go away and subscribe to the podcast. We're already sketching the blueprints. Nathan, let's talk about pan-stars. Is it just an asteroid harvesting machine or a tool that can actually help us find signals?
Both. Pan-STARRS is a set of wide-field telescopes with massive cameras that scan the sky every clear night, catching anything that moves or flares. Asteroids, comets, supernovae, fast transients. The secret is large field plus frequent revisits and automatic difference photometry. Subtract yesterday from today and see what changed.
Sounds like a perfect surveillance camera, but SETI needs a signal, not just something changed.
True, Pan-STARRS uses second-to-minute exposures, great for minute-scale flashes, but nanosecond laser pings get averaged out. Still, it offers 2 big advantages for SETI. 1, it builds a continuous event stream across huge sky areas, ideal for spotting suspicious optical transients, unusual shapes, repeatability, too clean curves. And 2, it provides instant triggers for fast response setups. See a flash, send an alert, activate telescopes with nanosecond detectors.
So Pan-STARRS is like a dispatcher, spots something weird and calls in the special ops.
Exactly. You can even add a narrow, fast channel, a small auxiliary photometer on one telescope with PMT and SPAD detectors and tight time sync. That way, the system takes deep images and listens for ultra-short pulses in the same field.
What signatures do we look for in this kind of data to separate nature from engineering?
Checklist. Repeat flashes from the same point over hours or days. Unusual transit morphology, angular or stepped shadows instead of smooth ones. Spectral purity, narrow bands or colors not explained by dust or plasma. And coincidence, confirmation from another site or wavelength. And timing alignment with exoplanet transit windows, temporal addressing.
What about false positives, satellites, planes, glare?
Plenty. So we need satellite ephemeres and track masks, algorithms for human-made trajectories, straight or zigzag paths, cross-checks with a second telescope and weather data correlation, auto-capture of raw time series on trigger, so we can analyze without smoothing.
So what's the biggest SETI advantage of Pan-STARRS?
Coverage and cadence. It constantly washes the sky and turns rare luck into statistics. For SETI, that means a better chance of catching a rare but repeating optical hello and redirecting fast detectors in time.
Next, we'll talk about how a similar approach is already working in Russia, the TAIGA HiSCORE project, what it can do with ultra-short flashes, and how to merge these schools into a unified night eyes network. Don't go away and subscribe to the podcast. We're getting even more hands-on.
Nathan, what's this TAIGA HiSCORE, and why is SETI whispering about it? It's not a classic telescope.
It's a field of photomultiplier tubes, PMTs, in Siberia, built for particle astrophysics. It detects ultra-short blue Cherenkov flashes from cosmic rays. The key, nanosecond timing and precise synchronization between stations, giving directional accuracy better than 0.1 degrees.
Translate that into SETI speak. How does it help with laser hunting?
HiSCORE already has what we need: very fast eyes, PMTs, large sky coverage, tight time sync across modules. Add narrow optical filters and coincidence logic, and the field becomes a trap for nanosecond laser pings.
How do we tell a cosmic ray from a deliberate pulse?
By geometry and spectrum, a cosmic ray shower gives a broad splash signature, while a laser is a compact front from a single sky point. Add coincidences in narrow filters and, ideally, confirmation from a second sight.
So TAIGA could join the optical SETI network.
Absolutely. Scenario: Pan-STARRS or another survey sends a trigger on a suspicious target. HiSCORE switches to fast mode and listens for nanosecond flashes. Or the reverse: HiSCORE detects a burst, sends an alert to optical or radio scopes for instant follow-up.
And what can we add to reduce false positives?
Double or triple coincidences across clusters, GPS or fiber optic time sync, satellite and aircraft masks, and auto capture of raw time series around the event, and a public archive with pipelines so the world can verify.
And the limitations.
Weather and sky background, the need for calibrations, dark frames, flat fields, and pulse calibrators, and the challenge of 24/7 operation. To catch rare pings, the network must always be on duty.
Wrap it in one line.
TAIGA HiSCORE is a ready-made fast vision platform. With a few upgrades, it becomes a powerful detector of interstellar winks in nanoseconds.
Next, we'll talk about results and prospects, what this kind of network has already shown, how to scale it to full sky coverage, and where to find the missing building blocks. Don't go away and subscribe to the podcast. The next chapter is just around the corner.
Nathan, no fanfare. These fast eyes, PMT fields, optical trap networks, what have they actually seen? Or is it another beautiful zero?
The honest answer, no confirmed artificial signal yet. But it's not emptiness, it's hard upper limits. We now know that in the observed sky sectors, there are no nanosecond flashes above a certain threshold. Plus, we've built a huge database of natural transients and refined our coincidence and filtering algorithms.
So not found is still a result?
Absolutely. We're narrowing the search space, which durations, energies, and flash rhythms are still possible. And we've built a confirmation standard, coincidences across modules and sites, precise time sync, and ʻOumuamua capture of raw time series around events.
Where does it hurt most? Funding? Hardware? Weather?
All three fronts. Coverage. We need nodes at different longitudes and latitudes to truly operate 24/7. Detectors, lower dark current, higher quantum efficiency, faster electronics. Infrastructure, stable GPS or PTP, satellite or aircraft masks, open pipelines for global verification.
Okay, what's the growth plan without dreaming of infinite budgets?
3 steps for the next 12 to 24 months.
Duplicate sites, at least 2 independent stations on different continents, false positives drop sharply. Hybrid mode, wide field monitoring, plus parallel fast channel, PMT, SPAD, SNSPD on selected fields, and Alert Hub. Any trigger gets sent within seconds to partners in radio, IR, and optics to instant candidate check.
I want metrics, not slogans. How do we know the network is maturing?
Hard KPIs, sky times time coverage, how much we've truly seen, number of cross-site coincidences, achieved energy threshold for pulses at a given distance, candidate verification time from trigger to conclusion, and share of public data and reproducible analyses.
False positives? That's a goldmine for training software. Are we using them?
Already doing it. We're building a noise library, satellites, planes, lightning, cosmic rays, and feeding it to ML classifiers. The more honestly labeled examples we have, the quieter the alert channel, and the faster we reach real candidates.
And finally, why make all this open? Isn't it easier to check and file away?
Openness is a safeguard against self-deception, and the only way to turn a headline into science. Raw time series, code, metadata, that's how any strong candidate can be independently verified. Only then does contact become fact, not folklore.
Perfect. Next, we'll talk about what changes if a signal really arrives, how to announce, who decides, and why euphoria is a terrible advisor. Don't go away and subscribe to the podcast. The sharpest part is coming. Let's imagine we've caught a real signal. What changes tomorrow morning for the average person?
Depends who's on the line. If it's a Type 1, a planetary civilization, the impact is mostly psychological and scientific-political. Space budgets rise, school books get rewritten, philosophical debates ignite, but daily life doesn't flip overnight.
So we get wow headlines, but life doesn't turn sci-fi?
Exactly. Their energy class is roughly ours, so no instant miracle tech. What we gain is direction and motivation, not blueprints.
And if it's a Type 2, stellar titans with a Dyson swarm,
Then the scale of possibility shifts. Just knowing it's possible to live tens of thousands of years shows that a technically and organizationally stable future is achievable. That could reshape economics, climate policy, and civilizational goals.
sounds like a coming-of-age moment. But many expect a tech package download. Is that realistic?
Most likely, no. Even if something is transmitted, it'll be complex, contextual, and possibly inapplicable without long adaptation. We underestimate the language gap and conceptual differences.
So the biggest myth is they'll say it, we'll copy it?
Exactly. What's more likely is a long decoding process. Signal structure, repeatability checks, attempts to anchor it to universal constants, math, spectra, geometry. It's years of quiet work, not a day of magic.
Okay, what definitely improves right away, even without blueprints?
3 things. Cognitive framing. We know civilizations can live beyond a century. That boosts our L in the Drake equation. Cooperation. Global projects gain new meaning, from telescopes to energy systems. Priorities. Shift toward sustainability, longevity, and open science.
Risks. There's always debate.
Risk number 1, self-deception. Mistaking noise, artifacts, or satellites for a hello. Solved by strict coincidence protocols and open data. Risk number 2, social turbulence, from mystification to geopolitical games over contact monopoly. Transparent protocols are key.
And the ethics. Do we reply or stay silent?
SETI's baseline consensus is first listen, then verify thoroughly and publish maximum data. Any reply only after international discussion on record. That prevents distortion and private diplomacy.
So to sum up, a found Type 1 inspires and boosts science. A found Type 2 could shift our trajectory,
But in both cases, we need cold method, not euphoria.
Exactly. Contact isn't the end of the movie. It's the start of a long project.
Next, we'll explore why decoding alien messages is a marathon, which universal keys actually work, and how to tell information from beautiful noise. Don't go away and subscribe to the podcast. The next chapter is almost here.
Let's say we've caught the one. What next? Press play, or is it more complicated?
Much more. First, we have to figure out where the message begins and ends. Synchronization, headers, timing. Then separate signal from formatting. What's code? What's error correction? What's just timestamps?
So before reading, we need to agree on language and markup. What do we usually latch onto?
Universals. Prime numbers, ratios of constants, hydrogen or OH lines, geometry. A good beacon starts with a shared key, repetitive, redundant, clearly structured. Only then comes the payload.
What if they send a picture or sound? That's visual, right?
Visual for us. They might have different senses, different natural encoding. Even with a picture, we have to guess. Row order, color depth, frame size, bit reading method. Otherwise, we get patterned noise and mistake it for abstraction.
Okay, format sorted. Why is this a marathon, not a sprint?
Because complex messages are compressed. There's minimal fluff and maximum context we don't have. We can detect structure, entropy, repetition, grammar, but meaning unfolds slowly. It takes years of cross-checks and hypotheses.
Here's the big question from a naive journalist. Will we get new physics?
Honestly, unlikely, quickly, or directly. Even if the message contains science, it's based on their tools, their error culture, their units. First, we'll grasp what's possible, that they exist, live long, and communicate. That alone reshapes our goals. As for reactor recipes, that's a long compatibility process, if it's even feasible.
What are the trickiest traps along the way?
3. Self-deception, seeing faces in clouds, solved by blind tests and independent teams. Spoofing or interference, satellites, artifacts, solved by coincidences and publishing raw data. And misreading meaning, mistaking cultural symbols for formulas, solved by patience and discipline. Structure first, interpretation later.
So the main value isn't the content, but the fact and the civilization's passport, right?
Exactly. The fact tells us L can be large, civilizations live long, communication works, and the meeting window isn't zero. That reshapes our risk models and century-scale planning.
Final thought for those listening on the subway. If we catch a signal, expect not fireworks, but a long, careful decoding with lots of checks, right?
Right. Contact is the start of an open-ended project. Verify, publish, build a shared dictionary, and move step by step. No promises of rewriting everything tomorrow.
Next, we'll talk about perspectives and existential pivots, why knowing they exist helps us navigate our own bottlenecks from climate to security, and why we need long horizons. Don't go away and subscribe to the podcast. The next conversation is built to last.
Nathan. It sounds lofty, but let's ground it. How does a single confirmation of extraterrestrial civilization help us when we're facing climate, war, and fragile energy systems?
It gives us 3 levers at once. A longer time horizon, the fact that they lived long, boosts our L parameter in the Drake equation, meaning longevity is achievable. Coordination, a real cosmic challenge, encourages countries to share data and budgets more effectively. And a goal hierarchy reset. Short-term wins lose value without resilient systems.
But people get tired of big words. What does this look like in policy and economics tomorrow?
We get boring priorities with high ROI, clean baseline energy and storage, closed-loop material cycles,
resilient networks with no single point of failure, and funding for open science and shared data standards. All of these reduce systemic risks across climate, health, and security simultaneously.
What about public psychology? There's risk, from messianism to panic.
That's why we need procedural coolness, verification, open archives, unified communication protocols. And alongside that, a new narrative. We're not the center, we're participants in a larger ecosystem of minds. That lowers toxic competition and raises tolerance for long-term projects.
A skeptic might say, okay, they exist, so what? Where's the tangible benefit?
It changes risk management. If we know civilizations can live tens of thousands of years, we gain a methodical goal: grow our L. Then budgets for threat monitoring, biosecurity, asteroid defense, they're not scare stories, they're investments in the chance to overlap with others.
And what about younger listeners? They want meaning, not reports.
That's a bonus, too. Contact breaks the feeling of progress dead end. Suddenly, there's clear motivation to study math, energy engineering, biophysics, because these are keys not to abstract contests, but to a shared dialogue between species.
Quick note on the risk of overhoping. How do we stay grounded?
Keep balance. No tech promises, only the promise of work, long-term, collaborative, transparent. And remember, any info bomb must pass through slow scientific filters or it'll be hijacked by politics and clicks.
Final line for commuters and headphones?
Knowing they exist isn't a magic key, it's a road sign. Long-lived civilizations are real, so our task is to become one of them.
Next, we'll explore how this knowledge reshapes our psychology and behavior, why even a type 1 confirmation gives us something to fight for, how to avoid euphoric spirals, and how to build decoding protocols without fanaticism. Don't go away and subscribe to the podcast. We're just getting started.
Let's say confirmation arrives. There are neighbors out there. Not sci-fi. What does that change, right at the level of breakfast and daily life?
It changes the mood. The feeling of none of this matters fades. A simple thought appears. Long life is possible. That means there's a reason to fix our own problems, from climate to education.
So not magic and warp drives, but clearer thinking.
Exactly. First, sober confidence. We're part of a bigger world, not the only spark. Second, priorities. Invest in things that work for decades, not just until the next headline.
People will argue, of course. Some will believe everything, some nothing.
That's why we need simple discipline. Open data, multiple independent teams, a clear log of what was seen and when. Fewer secrets equals fewer meltdowns.
And in everyday life. Schools, universities, culture.
In schools, basic astronomy and critical thinking as hygiene. In universities, combos like language plus info theory plus biology. In culture, less center-of-the-universe posture, more respect for long timelines.
Religion and philosophy, will they explode?
It'll be heated, but not necessarily painful. Many traditions already allow for other worlds. The key is not to privatize the topic and to speak honestly about what we know and what we don't.
And expectations. People will want a universe manual by next week.
We need to say up front, this is a marathon. First, confirm the signal is real. Then, slowly build a shared dictionary. No promises of everything changes tomorrow.
So the takeaway is simple. Knowing we're not alone isn't a one-day celebration, it's a multi-year plan.
Exactly. It's a reason to regroup, build resilient systems, and avoid extremes.
Next, we'll talk about post-contact practice, how to allocate telescope time, how to set up red teams for verification, and which common mistakes ruin good signals. Don't go away and subscribe to the podcast. We're staying practical. Nathan, no grand speeches. Who should actually be driving the search for extraterrestrial civilizations? Can scientists and volunteers carry it, or will governments finally wake up?
Everyone, in their role. Scientists bring methods and tools. Industry provides hardware and software. Citizens contribute via distributed computing and small observatories. Governments offer long-term funding and open infrastructure.
Sounds logical, but politics runs on 2 to 4 year cycles. How do you sell a decades-long idea?
Simple. We're not buying a guaranteed signal. We're paying not to miss one. Plus, there are immediate bonuses: new sensors, better communications, smarter algorithms, stronger education. This isn't a space toy. It's R&D with side benefits.
So the pitch isn't cosmic romance, but practical impact?
Exactly. We need KPIs, sky coverage times time, sensitivity, verification speed, share of open data. Politics loves spreadsheets, so we give them spreadsheets.
How do you explain to voters that the result might come after their lifetime?
With honesty, it's a marathon, but every year the network improves and every null result shrinks the unknown. Like medicine, prevention is boring, but it saves lives.
Okay, and money? Where do we find it without space ate the budget?
Use commensal modes. Listen while telescopes do other science. Deploy low-cost distributed stations. Build shared data clouds. And tap private foundations. They've already shown they can move fast.
What can we do this year?
3 steps. Expand open archives and build a shared alert hub across radio, optical, and IR. Deploy cheap, fast detectors in 2 or 3 new global locations, and launch education tracks, schools, universities, amateurs, so there's a trained watch team.
And if politicians still say, not now?
Then show the side benefits. Better interference filters lead to improved telecom. Ultra-fast detectors, medical and security tech. Open data leads to new startups. Stay the course. Opportunity windows come in waves.
So right now, we're laying the foundation, and the big discoveries come when the network matures.
Exactly. In 10 to 20 years, we could have global night vision, but we have to start building it today.
Final thought for the kitchen table?
Don't promise miracles. Ask for stability. Regularity and openness make the miracles happen.
Next, we'll talk about the global bifurcation point, why the world can pivot from small decisions, and how not to miss the right fork in the road. Don't go away and subscribe to the podcast. We're heading into the heart of it.
Nathan, you often say we're at a fork in the road. Sounds dramatic. What does that mean in plain terms, and why now?
A bifurcation is when small decisions push the system toward very different futures. Economy, climate, tech, security, they're all intertwined, and the system's sensitivity to small stuff has increased. Add new risks, bio, cyber, AI, and the trajectory becomes unstable and nonlinear.
Okay, but how do we know this isn't just a headline? Are there signs we're really at a snap point?
Yes, we're seeing frequent, rare events. Black swans aren't rare anymore. Supply chain distortions, energy market spikes, info wildfires. The system's faster, but the buffers are thinner. That's a pre-bifurcation state.
So what do we do? Not in theory, but hands-on. Give us a short list.
4 steps. Redundancy and backup. Energy, comms, data without single points of failure. Monitoring and early alerts. Data standards, open dashboards, shared alert protocols. Red teams, groups that professionally break plans and find weak spots, and small experimental launches. Test small, scale only what works.
And where does space and our neighbors fit in? Isn't that a different league?
It's directly connected. If we know long-lived civilizations exist, the goal is clear. Increase our L, how long we last. That makes asteroid monitoring, clean energy baselines, open science, and resilient networks not hobbies, but part of the route through the fork.
Where do we most often fail at the fork?
2 extremes, euphoria It'll fix itself and panic, lock everything down. The working mode is calm regularity, small but steady improvements, transparent metrics, a shared risk vocabulary, and no miracles by Friday.
So the kitchen table recipe is make systems thicker, data cleaner, decisions smaller and more frequent.
And add a long horizon. The ones who pass the fork aren't the loudest. They're the most resilient and patient.
Next, we'll talk about our special zone in the galaxy, why we might be observed but not interfered with, and how that's explained without mysticism. Don't go away and subscribe to the podcast. We're continuing with clarity, not drama. Nathan, let's cut the fog. If they exist, why hasn't anyone come to fix our climate or roads? Where is everybody?
There's a simple, non-mystical explanation. We're in a bottleneck phase, a short, critical stretch of evolution. We might be observed, but not interfered with to avoid disrupting the experiment. It's called the zoo hypothesis, not because we're animals, but because interference ruins the data.
Sounds poetic, but what's the foundation beyond romanticism?
3 solid motives: causality and safety. Any miracle intervention creates unpredictable consequences, including our reactions. Observer ethics. Don't touch a system while it's learning to walk. And signal-to-noise integrity. If the goal is to study how a civilization navigates the bottleneck, interference makes the data useless.
So no one should save us, because then we won't know if we can save ourselves?
Exactly. And there's a practical angle. If the elders see we're almost capable, they'll let us try. It's like an exam. A hint ruins the point of assessment.
Then why no hints at all? Not even a like on humanity's post?
Hints might be extremely subtle. Passive markers in data, like a clean technosignature without contact. Discovery windows when we're ready. Brief winks, no intervention. Or total silence until we reach stability and become viable for two-way contact.
Sounds harsh, but why would they care about us at all? What's worth watching?
The bottleneck is unique. One planet, one shot to go from raw exponential growth to sustainability without self-destruction. It's rare cinema, even galactically. Others may have filmed hundreds of seasons, but our script is still original.
Okay, practically, if we're being watched, what should we do?
Exactly what boosts our longevity. L. Clean baseline energy, closed material loops, open science, resilient networks, and honest metrics. And don't wait for wizards. Their plan is not to interfere.
And finally, how do we avoid falling into a cult of invisible curators?
Stay focused on the verifiable. Any observer hypothesis is only useful if it improves our actions without demanding belief. No metrics, no discussion.
Got it. Next, we'll talk about strange signal archives, what the wow signal really was, why it still stirs minds, and how to tell a real wink from instrument quirks. Don't go away and subscribe to the podcast. Things are heating up.
Nathan, let's be honest. Once a week, someone sends me proof of UFOs. What does science actually have on the table? Not blogs, but data.
If we're talking about verifiable evidence, then in the major NASA ESA archives, there's nothing solid on flying saucers. Lots of noisy videos, very little raw telemetry, and almost no coincidences across independent platforms. Science likes a triple yes. Different sensors, same signature, reproducibility. Here, it's usually no.
So UFO still means unidentified, not extraterrestrial.
Exactly. Unidentified usually means bad calibration, satellites, plasma, optics, or software artifacts. Until we have raw data and independent replication, it's not a craft, it's a question.
Okay, what about ʻOumuamua? That wasn't TikTok. It had telescopes, trajectory, and anomalous acceleration. Alien calling card or boring physics?
It's a genuine mystery. Facts: small object, no visible tail, but slightly non-gravitational motion, like a faint push from something without the usual gas plume. Possible explanations: a light sheet or porous object, Solar pressure gives a tiny nudge. Unusual ices, CO, CO2, H2, etc., sublimating without dust, hence no tail. Tech hypotheses like a fragment of a sail. These are working ideas, not proof. Key issue, we had little data. It flew by, waved, and vanished.
So we're not debating aliens. We're debating image quality and sublimation physics.
Exactly. If we want truth, we need to catch up. That's why people are discussing intercept missions for future interstellar visitors. Fast navigation, imaging, spectra, dust, gas, and we settle the question with data, not memes.
Okay, now 3IATLS. You've said it's a rare guest, water heard from afar, weird spectra, anti-tails. Is it more quirky comet or ʻOumuamua 2.0?
More like a quirky comet. We see water via OH in UV, CO2 as a strong driver, odd tail behavior, and even nickel lines in the gas envelope. All interesting, but within natural processes. Tech hypotheses are discussed as extremes, but the working model is an exotic but natural comet. And unlike ʻOumuamua, we have lots of instruments on Atlas and more data coming, so uncertainty will shrink.
So the plan is simple. Don't argue forever, collect meters of raw data.
Exactly. And kitchen rule, if an event can't be rechecked, it doesn't live in science. That's why the real UFO agenda isn't clips, it's interceptors for interstellar objects, wide optical and radio networks, and open archives.
Okay, takeaway for those stuck in traffic. UFO doesn't mean aliens. ʻOumuamua is a real mystery with too little data. And 3IATLS is weird, but naturally weird. And the grown-up move is to fly toward the next visitor.
Exactly. We can argue for years or put engines on the problem and close it with close-up shots.
Next, we'll talk about how to actually intercept such objects, what propulsion can realistically reach them, why missions must be planned in advance, and how to stay on budget without a magic wand. Don't go away and subscribe to the podcast. We're getting practical.
Nathan, let's forget past visitors. Right now, we've got 3I Atlas, a live interstellar guest in the news stream. Why should we chase it now instead of just watching from afar?
Because this is a closing window. It's the third confirmed interstellar object, already showing water via OH in UV, strong CO2 activity far from the sun, strange tail-anti-tail geometry, and even hints of nickel in the gas envelope. Mars orbiters have already imaged it, and post-perihelion data is coming. If we get close, we can settle a dozen debates with facts, not theories.
What exactly do we need to see up close to calm the hotheads?
4 things: composition and isotopes, spectra of H2O, CO2, CO, metals, and isotope ratios, a fingerprint of its native disk, dust and grains, size, polarization, albedo, helps explain the anti-tail to tail transition, nucleus, shape, rotation, active cracks, jet map, and thrust versus gas. If there's non-gravitational acceleration, we measure mass loss and check if it matches the visible gas cloud. If thrust exists but no cloud, that's a strong argument against a normal comet.
Sounds like we should have launched yesterday. Is it doable without sci-fi?
Yes, if we play the long game. 2 options. Hot intercept, fast launch with solid booster and kick stage, distant kinetic dust probe, mini spectrometer on flyby. It's a grab-and-go mission. Or permanent ambush. Keep a standby interceptor in heliocentric orbit with solar electric propulsion, radiators, and high delta V. When the next 3i pops up, it adjusts orbit and meets it. Cheaper on average and works every time, not just once.
Minimal gear to avoid breaking the bank?
A 4-block mini-mission. Optics and near-infrared, water CO2 lines, dust, photometry, UV channel for OH, direct water proxy, dust capture on flyby, aerogel or shields, gives grain size and mineralogy, relay and DSN-compatible link and precision clock for targeting and Earth-based coincidence. Mass is tight, power via solar panels, imaging lasts hours, science lasts years.
Okay, and what would observers, if they exist, think of us poking a guest with a camera?
Most likely they won't interfere. If we can independently plan, intercept, and analyze, we become predictable and safe. That's a signal of maturity, not aggression. Panic, conspiracies, and bans, those signal immaturity.
Quick summary for those driving. Why spend effort on 3i Atlas instead of waiting for the perfect object?
Because perfect ones don't follow schedules. Atlas already gave us water far from the sun, a CO2 engine, rare tail geometry, and a pile of anomalies. One close pass and we move from guesses to hard numbers. Plus, we build a repeatable protocol: early detection, fast launch, standard sensors, and open archive.
Final question. What would need to happen this season for you to say, case closed?
Combo of confirmed mass and brightness matching measured gas output, jet map explaining anti-tail to tail, isotope ratios fitting a natural origin, or detected acceleration without gas, confirmed by independent instruments. The first stamps it natural but exotic comet. The second triggers a serious technosignature check.
Next, we'll talk about quantum topics without the magic, where entanglement actually helps in signal hunting, and where it's just a beautiful myth. Don't go away and subscribe to the podcast. We're heading into the sharpest edges. I'll admit it up front, quantum physics confuses me. Help me sort it out. Can quantum actually help us communicate with someone out there, beyond the stars?
Short answer, no. Quantum entanglement isn't a faster-than-light phone. It's about strange correlations between particles, not sending a message like, "Hi, we're from Earth."
Wait, I've heard of entanglement. Two photons are linked. Touch one, the other feels it. Isn't that a message?
It feels like it, but here's the trick. The person looking at their photon sees random results. To realize they were magically correlated, you have to compare notebooks via a regular channel: mail, radio, laser. Without that comparison, it's just noise. So to get meaning, you still need a classical channel, limited by the speed of light.
So quantum mind teleport is a pretty fairy tale.
Exactly. Entanglement is like two dice that somehow always rolled the same number. Cool, but you can't build a sentence from that until you sit down and compare rolls.
Okay, what about quantum consciousness? I keep hearing the idea that the brain is an antenna tuning into the universe.
The brain is warm, wet, and noisy. Quantum delicate states decohere almost instantly in that environment. Neuroscience explains signal transmission through electrochemistry and classical biophysics. No thought teleportation or Wi-Fi to the stars.
All right. And the many worlds interpretation, where there are a million Emmas and Nathans. Can we wave to them?
Even if branches exist, there's no channel between them. It's a way to calculate probabilities in quantum mechanics, not a tech to send letters across realities. No bridges, sorry.
Then where is quantum actually useful in the real search for signals?
In the tools, and that's powerful. Detectors, superconducting single photon counters, or SNSPDs, and other quantum sensors detect very faint laser flashes. That expands our hearing range. Timing. Quantum frequency standards, or ultra-stable clocks, allow nanosecond-level synchronization between observatories. Without shared time, coincidence detection falls apart. And channel security. Quantum key distribution, or QKD, enables secure data links between observatories and archives, fewer risks of tampering or human noise.
So quantum isn't a portal, it's better glasses and better clocks.
Exactly. See fainter, measure sharper, sync tighter.
And quantum computers? People love to say, turn one on and we'll find aliens.
They're useful as analysis accelerators, data compression, weak pattern detection, hypothesis testing, but they don't open a new communication channel.
They're turbo magnifiers, not magic radios.
Could we imagine a quantum signature from aliens? Like, if we see entangled photons, it's them.
That's a slippery slope. Entangled states can be naturally produced, for example in some astrophysical processes. A reliable technosignature is something nature struggles to make. Narrow, ultra-short laser pulses, a repeatable rhythm, timing addressability, like during a planet's transit, when the target is clear. Also, complex modulation that clearly carries structure, not just an energy pop.
Give me a home test. Someone says they answered me through entanglement. What do we ask?
5 simple things. Raw data, show time series, not screenshots. Independent sight, who else saw the same thing at the same time? Calibrations, how did you rule out instrument artifacts and satellites? Repeatability, did it happen again under the same conditions? And classical channel, is there confirmation without quantum magic? Laser, radio, archives. If these aren't answered, it's a story, not science.
Great. Now the flip side. What do we want to catch to say, this looks intelligent?
Dream candidate, a series of nanosecond optical pulses from one point, seen simultaneously in 2 observatories with a stable interval, like prime numbers, in a narrow spectral band and ideally timed to the transit of a known exoplanet. That kind of wink is too precise for dust or plasma.
And the final nail. Explain without formulas why we can't send a message faster than light, even a single word.
Because meaning needs structure. Where's the start? What's 0 or 1? How do we sync? Entanglement doesn't give you controllable zeros or ones, just random results that only gain meaning after comparison via a classical channel. And that channel is limited by the speed of light. That's it.
So no cheat code of the universe.
Our cheat code is discipline. Good detectors, precise timing, independent checks, and open archives. Less magical, but it works.
Next, we'll talk about earthbound contacts, how to assess eyewitness stories, what makes a good faith case, and why without raw data, every encounter is just a tale. Don't go away and subscribe to the podcast. We're keeping it honest. Nathan, contact stories are eternal drama. Skin marks, sky flashes, communication. Let's skip sarcasm and romance. How are these cases actually investigated?
Like an aviation incident, procedurally with data custody and independent replication. We separate 3 layers: observation, what was recorded by instruments and eyes; witness interpretation, what it meant to them; and source hypotheses, nature, tech, psychophysiology, etc. Mistakes happen when people jump from 1 to 3, skipping 2 and verification.
Let's start with raw material. What counts as usable data?
Original files, not forwarded copies, EXIF metadata, precise UTC time, coordinates, azimuth and elevation, camera settings, exposure, ISO, focus. Also, radar or ADS-B screen recordings, satellite TLEs, weather reports, geomagnetic conditions, and a second independent sensor, security cam, another site, radio channel. Without a second eye, it's not contact, it's a case for review.
What do you do with video and photos?
3 quick tests: photometry and star calibration, brightness, color, distance, speed estimates; geometry, landmarks, parallax, angular size versus moon or buildings to honest scale; and optical artifacts, glare, bokeh, rolling shutter, autofocus, sharpening. 70% of triangles are defocus and lens flares.
And with people, witnesses are emotional.
We use cognitive interviewing, free narrative to open clarifying questions, to reverse timeline playback. No prompts like, was it a triangle? We log duration, motion direction, sound or no sound, and ambient light sources. We separate what was seen from what was thought.
What about physical traces and sensations?
always psychosomatic?
Not a label, a diagnostic process. We document medically, photos with scale, dermatoscopy, tests for contact dermatitis, UV or thermal exposure, chemical residues. Parallel track is sleep and stress. Sleep paralysis, hyponagogia, PTSD can produce vivid presence episodes. These must be ruled out before discussing external agents.
What earthly sources most often mimic contacts?
Top 5. Planets, ISS or bolides, surprisingly common. Satellites or Starlink or Christmas trees in fog. Drones or aircraft outside corridors and spotlighting. Atmospheric optics, light pillars, second suns, thin cirrus effects. Camera optics, flares, auto exposure, ISO jumps. Plus human error, misjudging distance and size without reference points.
Are there cases that pass all filters and remain solid?
Yes, but the honest label is UAP without attribution. Not alien, just insufficient data or coincidence. We use such cases to improve the network. Add synchronized optical and radio, include spectra and polarimetry, tighten time sync.
You've said contact data custody a few times. Why so strict?
To prevent contamination. First, we make a bit-for-bit copy of the original into a secure archive, hash it, log who accessed it and when. Any enhanced Photoshop version lives separately. Otherwise, we're debating processing artifacts, not the event.
Give an example of a bad case that sounded convincing but collapsed under data.
Floating fire over the city, changed shape, seen for an hour. At UTC, Venus was 10 degrees above the horizon, thin haze created a halo, and movement was a camera shake illusion on digital zoom. Once we anchored to stars, the shapes vanished. It was optics and atmosphere.
And the opposite, a case where everything was honest, but we still don't know.
2 sites, synchronized timestamps, silent object, clear angular track, but no spectrum, and the third channel wasn't activated in time. Result, UAP. Next step, install permanent monitoring post, add auto alerts, cross-check with aviation and satellite telemetry in real time.
Can we define credibility levels so the public understands the scale?
Yes, here's a useful ladder. L0, story without data. L1, data exists but no originals or metadata. L2, originals and basic checks passed. L3, independent coincident site. L4, multimodal, optical plus radio capture with unified time base. L5, repeatability and predictability. Levels L3 to L4 are rare. Most viral stories are L0 to L1.
Where do authors most often break their own cases unintentionally?
3 common mistakes. Forwarding via messengers, EXIF gets wiped. Editing contrast and sharpness before analysis, adds artifacts. No landmarks in frame, can't judge scale or speed. Rule, don't touch anything, shoot short bursts, keep the horizon, building, or moon in frame.
Why are public archives, red teams, and external audits so important?
Because self-deception is normal, not rare. Open raw data, reproducible external analysis, red teams that professionally break pretty stories, that's insurance. If contact ever happens, it must survive independent re-verification.
Final takeaway for those listening in traffic.
Science separates experience from source. 90% of cases fall to natural, technical, or perceptual causes. The rest are data gaps, not proof of extraterrestrial. Observation network quality matters more than any dramatic story.
Next, we'll talk about the risks of extraterrestrial information, how even a real signal can cause harm if misinterpreted. why red teams are essential, and which publication rules reduce fallout. Don't go away and subscribe to the podcast. We're staying sharp and serious.
Today, no romance. Let's say we've received a real signal, or even a file, an image, a block of code, a set of formulas. Why is that dangerous? Isn't it just knowledge?
It is, but it can also be an info hazard. I break the risks into 6 buckets: misinterpretation, seeing patterns where there's noise; technogenic risk, harmful instructions, mat software that can be replicated; cyber vector, the package as a carrier of exploits; socio-psychological shock, panic, cults, politicization; poison data, deliberate disinformation that wastes resources; and legal and ethical vacuum, who's responsible for publishing, harm, and access.
Let's unpack that. What are dangerous instructions in scientific terms?
Any information that significantly lowers the barrier to causing harm, recipes for toxin synthesis, ways to bypass biomonitoring, schematics for disrupting critical infrastructure. Even harmless formulas can become ready-made protocols in the wrong context.
And the cyber vector, is that sci-fi?
Very real. The gift arrives as encoded data. We run it through a visualizer or decoder and trigger an exploit. So the first rule is cold handling: offline, air-gapped, one-way data buses, unknown format checks, sandbox isolation with full system call logging.
Okay, what does a proper protocol for handling such a package look like?
3 layers of protection. Layer 1, technical quarantine. Air-gapped lab, clean machines, one-way data loading only. Hash chain and access log: who, when, what was copied. Multi-format scanning, binary parsing, cross-interpreted by different parsers. Behavioral sandboxes: what does the code or model do when run? Every system call under the microscope. Layer 2, analytical filter. Red teams, independent group tasked with breaking the pretty hypothesis and finding harm. Blind analysis, part of the team works without knowing the romantic version to avoid confirmation bias. Multi-channel replication, optical, radio, IR from different observatories, time-synced. Layer 3, publication protocol. Stage disclosure, first metadata and method, then safe excerpts, full release after risk assessment. Cryptographically signed data and code versions to prevent tampering, and maintain feedback channels. Anyone can submit counterarguments or errors, and they're logged publicly.
Sounds slow and boring, but okay, what about society? We're not in a vacuum.
That's where risk communication comes in. Honest expectations, preliminary, unverified, analysis ongoing, no speculation. Open timeline, when and what will be published, where materials live, and how to submit independent reviews. Anti-cult framing, not leaders revealed the truth, but procedure and data. Psychological buffer, trusted voices from science, religion, culture, who translate complexity and dampen extremes.
Give an example of how even a good publication can cause harm.
We publish raw matrices as is, and they contain embedded language that activates code in an interpreter. Or we release an overly detailed protocol, and the next day dozens of garage labs try something dangerous. Or we headline, "All models of the world are obsolete," triggering a political storm, grant freezes, and broken collaborations.
What does safe publication look like without censoring the truth?
Publish method, verification criteria, control samples, and an interface for external replication. Remove operational details with direct harm potential, bio, materials, IR security, and clearly mark what was removed and why. Cryptographically signed data and code versions to prevent tampering. and maintain feedback channels. Anyone can submit counterarguments or errors, and they're logged publicly.
And if the package is semantic content, a message, lecture series, ethics, what's the main risk?
The main risk is social engineering. We tend to see authority from above and adopt decisions without local context. We need multi-layered expertise, philosophers, cultural scholars, lawyers, engineers. And a hard rule: no actions based on advice from the message until multi-party evaluation of consequences.
Historical analogy to make it click?
In the vacuum tube era, cockroaches crawled into chassis, got fried, and crashed the machines. No one intended it, but environment and design created an unexpected vulnerability. Same with extraterrestrial info. Even without malice, context mismatch can short the system.
What should we prepare in advance before any contact?
Quarantine infrastructure, air-gapped labs, tool stack, data custody protocols, teams, white, red, blue, builders, breakers, defenders, publication rules, stage disclosure, ethics boards, external auditors, legal scaffolding, international agreements, liability insurance mechanisms, educational contour. Teach society that slow is safe.
Final takeaway in one sentence.
Extraterrestrial information isn't a gift under the tree. It's an unknown device. Before plugging it into the grid, we need to take it apart, check for shorts, and only then power it up. Buy the manual under supervision.
Next, we'll talk about how to build signal interception and decoding teams, from the role of amateur observatories to distributed supercomputers, and why it's all quietly run by the essential dispatcher of doubt. Don't go away and subscribe to the podcast. We're heading into the most practical ground. Nathan, we're at the finish line. 50 episodes from the first replicator to interstellar visitors. If you had to pick one scientific nail to hammer into the wall of the universe, what would it be?
Surprisingly down to earth. Why is the muon to electron mass ratio exactly what it is? In plain terms, why is the light particle family tuned just right for chemistry and stars to even exist? If we crack that, we'll understand why matter's blueprint chose these numbers and where the edges of possible universes lie. It's the same thread that runs from genetic code to the multiverse. If the rules aren't random, we might be able to explain them, not just accept them.
Sounds like a scientist's honest manifesto. Fewer guesses, more reasons. And as for life in the universe, are you still firmly in the it's out there camp?
Absolutely. The cosmos is vast. Chemistry is universal. And we're already seeing interstellar comets delivering water and volatiles. ʻOumuamua left us with questions. 3I-ATL brought answers and new mysteries. The odds that somewhere biology emerged are well above zero. Our job is to build instruments, not myths.
That's exactly why we spent so much time on protocols, how to catch signals, how not to mistake noise for wonder, how to safely unpack a package. It's the boring part, but it's the bridge from speculation to knowledge.
Totally. Protocols are civilization in action. Open archives, independent verification, red teams, honest credibility levels. If you want contact, earn it through reliability. If you want truth, put it through a stress test.
And the human part? We won't know who's out there until we figure out who we are. Smoke-free energy, science without locked doors, networks without fragile bottlenecks. It's not about romance, it's about durability.
And also about joy. When you spot a thin OH line in the spectrum of 3I-ATL, you realize that's water from a distant nursery. And suddenly it's clear we're not chemically alone, which means the search has meaning and momentum.
Friends, if this long conversation was meaningful to you, subscribe, leave a rating, share the episode. It matters that these deep dives stay public and calm. Let us know what resonated most. First replicators, panspermia, quantum without the magic, or the Ambassador Comet Atlas.
Thanks for walking this road with us. We'll keep going. More data, more field missions, more verifiability. And yes, one day we'll say,
This isn't a hypothesis. This is proven.
Protect your curiosity. It's the best engine we've got. Don't go away and subscribe to the podcast. New seasons and new windows into space are just ahead. Goodbye and see you soon.